Yes.
Okay, so welcome everybody. Hope most of you are as excited as we are to be here. We are in the 5th Continual Learning in Computer Vision workshop, and I will very briefly give an overview of how the workshop will be organized. And then we will have 2 talks now in the morning before we move on to the first coffee break. So, I mean, as you know, continual learning has been gaining some traction over the last years. More papers have been published on different directions. And basically, the base idea is overall trying to learn new tasks on a model or add new concepts to a model, while you are restricted on how much data you have from previously learned tasks, and you want to learn it like referencing the plasticity of the model while trying to maintain the stability, which is trying to not forget what you've already learned, unless you want to, right? Like now some more papers are also pointing out that different types of distribution shifts. So maybe today we will have some nice ideas on the direction. The workshop had many submissions on several of the topics that cover in continual learning. I will encourage everybody later to go to the poster sessions where we have like 30 plus papers on some of these topics. And the idea is that lately we've also been seeing a bit more papers trying to explore more connections or having a bit more interdisciplinary ideas from some of these subfields, let's say, like from domain adaptation, out of distribution, open world learning, and trying to connect them and make it a bit more interdisciplinary, going towards agents that are lifelong learning agents, right? That can have multiple of these capabilities. Overall, the workshop will be divided as now I'm giving the opening remarks, then beneath here we'll give a talk. We've had a bit of a last minute change, so Hava Siegelman will be giving her talk online now instead of in the afternoon. Then we will have a poster session and a coffee break where, again, I encourage to go see some of the posters. They're very nice work. Then we will have 2 more talks by Liyuan Wang and Shen Zhao. We will have our first paper oral presentation from Eden Beluada, which will be online in this case. Then we will have the lunch break, 2 more talks by Amal Ranentriki and Elisa Ritchie. We will have the panel discussion with 4 already invited speakers. Beneath here, Liyuan, Amal, and Elisa, where we will also encourage all of you to propose questions for our panelists that we can discuss about how continual learning has been evolving, will evolve, and maybe some ideas on interesting concepts that are emerging. Then we will have the second poster session, and right after, Jedras here will present the second oral presentation of the day. And we will finish the day with the report from the competition challenge. We had a competition going on the last months with continual learning with repetition and unlabeled data, which we think is a quite newish scenario that might be of interest to some of you. And Gianluca here will give a recap on how the challenge went, and we will see the presentations of the 4 top winners. And finally, we will give the best paper award, and we will close. And yeah, that's it. Here are the speakers that we will have, as I was mentioning them before. There is a random ordering now of hours on where they will be, but you have the program on the website also. We are very happy to say that this year we had a lot of submissions. We had 45 submissions. We had 15 accepted papers that were onto the archival track, which get into CVPR proceedings, and we had 18 accepted papers that were into the non-archival track, which conform a variety of papers that just wanted to submit to the non-archival, but also papers that have been accepted in the main conference or in main conferences during the last year, and that they want to disseminate their work, so that they will also be some of them in the poster session. We will have the 2 oral presentations that we were saying, and the best paper award at the end. Regarding the challenge, as we were saying, we will have Gianluca talk more in detail about it. But in general, like as I was saying, we were mixing up class incremental with repetition with the use of unlabeled data. So we will talk about having two streams of data, one with labeled, one without labels, and how we can manage them over a series of experiences or learning in a continual manner in a better way. And the 4 best performing teams will present their approaches. If you want to participate, I mean, most of you are already here or online. Welcome also to all of our online viewers. You will have all of the information that you need also on the website of the workshop. Here is the QR code for it. With the program, although remember that Haba and Amal have switched places. And that's the only change from the program that we have to. Okay, I would like to also thank all of the organizers. Gianluca and Benedict are here, and myself. Like, feel free to come to us over the next days if you're here. We're very enthusiastic about talking about continual learning. They are starting PhDs, so they are very hungry for maybe some opinions. So please ask them about their ideas and maybe share your own and make this a nice first experience of CVPR for them. All of the other organizers were very nice on helping set up the talks, the sponsors, and everything. They sadly cannot be here, but they also probably will be happy to receive emails if you want to share some continual learning ideas. We are all very passionate about the topic. We also would like to thank all of our reviewers. I mean, all of these submissions could not be done and reviewed properly without the help of our reviewers. So thanks a lot to them too. And finally, our sponsors, because we had Continual AI helping a lot with setting up all of the logistics on the website and hosting the code base of the dev kit of the challenge. We have Matrix sponsor the Best Paper Award prize, and then Apple sponsor the challenge and competition award also. Okay, hope you enjoy the workshop. Welcome everybody, and let's start with our first speaker, Vineet.
Do I have Zoom too?
Oh, yes, probably. Do you have the link?
If you can email the link,
I can share it now. We'll need to put both the okay. You should have an email now from
we supposed to hear anything?
Sorry, we are setting up the speaker. We will take just a moment.
Ah, okay, no problem.
Okay. Thank you. Okay. Well, Vineet is professor of the computer science and engineering at the Indian Institute of Technology of Bharat, right? And you've specialized in machine learning, computer vision, explainable AI, right? And you've been doing continual learning now for some time. A few years. And thanks for coming, and please.
Thank you. Thank you for having me. I think
It's not sure.
because I see the person to you. I'll switch them. I'll switch them. By any chance, does anyone have a USB to HDMI just in case this is the problem? This it should also work. Is that right? This one works? Oh, okay, awesome. Okay. Let me do one thing. Let me just share it the green screen because I think I may have to. I think if I swap, I think I know what I may have to do. I may have to duplicate the displays. Yep. Maybe I can see if I choose which display. Okay, I think I may be able to do. Let's stop sharing. Now let's choose this display for. Let's see if that works. Okay, see. This is the okay, let me see. We have to mirror that. I thought I mirrored it. You have to actually zoom to share a screen, not a like program. No, I think I may have to mirror the displays. So to ensure that, I'm just trying to see. If I can. Let me see. So, sure. What?
You know, same thing, and this is full swap display option. And
Yeah, the problem is it's swapping. The Zoom is sharing one screen and projector is sharing. That's the problem.
okay. You can directly share this. Like you can click on the share link and then just share the window that you want to share.
Yeah, that's what I'm doing.
Okay.
But it's sharing what is showing on my screen.
Okay.
And it's presenting because there's a sharing on Zoom going on and a projecting here going on. That's the catch. Yeah, thank you. Thank you.
Share the whole window.
That's what I've done, but it's sharing my window. It's sharing my window. Desktop too. So I think we're good. I think we're good.
Now we need to
Yeah.
Yeah, that's one.
Perfect. So
There we go. We continually learn. Okay, great. Apologies for that. Just keep it up. Yeah, apologies for the initial hiccup. Good morning, and thank you for showing up early on a cloudy morning, still early into the conference. So thank you for joining this talk, and thank you for the organizers for having me here and give a talk on our research at this workshop. So the quick TLDR of this talk is going to be, I thought I should start with this, is obviously, as Mark just mentioned, continual learning is becoming more and more significant and popular, and people are trying to address it from different settings, newer tasks, newer classes, newer domains, so on and so forth. But then when you talk about integrating continual learning in real-world applications, we need to start thinking about layers of responsible AI, like explainability, privacy awareness, privacy preservation, so on and so forth. So we've been doing some initial work in this direction. So the purpose of this talk would be to share what kind of challenges we encountered and what could be some ways to develop methods towards explainable continual learning or privacy-aware continual learning. Okay, that's going to be the TLDR of this talk. Since I'm the first speaker, just a quick couple of minutes. I know Mark already spoke about it, but I'm quite sure all of us agree that the last 15 years, the success of machine learning and deep learning has been thanks to supervised learning paradigm. Now we know that with large amounts of curated, annotated data, we can train models that work effectively in the real world. But what we ideally want are models that continually learn over time with newer data without having to train from scratch every single time. And that has led to continual learning, and which borrowed from human learning is the constant development of increasingly complex behaviors and the process of building more complicated skills on top of those already developed, right? And the primary challenge in moving from supervised learning paradigm to a continual learning paradigm, which could be the stratum for all kind of developments going forward, is catastrophic forgetting. And this goes back to the late 1980s when a couple of researchers, McCloskey and Cohen, showed this phenomenon on very simple neural networks. I'm not going to go into the results here, but their main results showed that when you compare human learning to learning of a neural network, both undergo forgetting, but the forgetting of a neural network is catastrophic when you compare to human learning. Okay, that's what they showed at that point in time. And over the last few years, primarily the last decade, there have been a wide range of continual learning methods that have been developed: model growing methods, parameter isolation methods, regularization methods, knowledge distillation methods, and rehearsal, which is a popular strategy to replay previous samples so that the model doesn't forget on those previous tasks, right? There's just one categorization. There are several other categorizations, and there are survey papers this year if you'd like to know more on continual learning itself. Regarding our own efforts in continual learning, we began a few years ago on trying to do continual learning for tasks like classification and detection. So some of our early efforts, let me try to see if the pointer works. Okay, some of our early efforts were on trying to come up with meta consolidation for continual learning, where we try to compress the model that you learn in a latent space and then decompress it for different tasks at runtime as required. Then we had an energy-based latent aligner where we try to align representations on a manifold of different tasks and push them to different parts of the manifold. We also had some work on cross-space clustering and controlled transfer. Once again, the goal was to kind of compact the representations across tasks into different spaces. A subsequent work that we did was trying to go towards what I'd like to call organic lifelong learning, where if you look at supervised learning, we know that we learn from a fixed data set with a fixed set of labels. Whereas if you contrast human learning, it's far more richer, where you learn from available data with or without labels. You refine using newer data without forgetting the past significantly. You can learn only from descriptions without actual access to data. You can learn interactively by asking questions. And very fundamentally, you also have the ability to say, I don't know, and ask for more information when you cannot categorize a given data point, right? And each of these have been attempted in machine learning in different settings. You have continual learning, you have zero-shot learning, you have active learning, you have open set, open world learning, and all of those have been addressed in different ways. So what we tried to do was try to see how do you put this together in a continual learning framework, right? So the purpose of continual learning is to learn from whatever data that you get at any point in time, right? But the moment you talk about different settings in continual learning, like class incremental, task incremental, domain incremental, you're again laying boundaries on how you expect the data to arrive. But in the real world, data does not tell you how it's going to come. Right? So what we were trying to do is how can you make the learning most organic in a continual learning world? Some of our initial efforts were open world object detection in CVPR 21, which was perhaps one of the first efforts on trying to do open world object detection, where we can call out an object as an unknown. And when you have the label information for that unknown, you integrate that into your model and continue to learn over tasks. Then we had novel class discovery without forgetting, where we once again had a continual learning setting, but you have newer data, which is unlabeled, where you'd like to call out the unknown in the newer data, but you also say how many kinds of unknowns are there, right? Which is something humans do quite effectively. Then we also attempted, how do you put zero-shot learning and continual learning together, where it's possible that as you learn over multiple tasks in time, a task for which a class was zero-shot, which means you had no data for it, could end up start having data and labels in a later task. And a class in that later task could be zero-shot, which could become once again few-shot, or maybe you have the full annotated data at a later point in time. You could have all of these complex combinations that could occur when you work with data in the real world. So we are trying to see how do you address these kinds of problems beyond just static settings within continual learning itself. Right? But that's the background that I wanted to set. But the rest of this talk is not going to be about these. I'm going to talk about two specific dimensions that we've been exploring recently. One is along inherently interpretable continual learning models. And the second work is on privacy-aware continual personalization. Right? So those are the two things I'm going to talk about. Once again, I'd like to add a note that these are exploratory efforts. These are initial efforts. And at this point, I'm just presenting this for sharing with the community and probably having some discussions and getting some feedback too, right? So let me begin with the first one, which is inherently interpretable continual learning models. I'm quite sure all of us in this room know that explainability in ML has exploded over the last few years. And there have been a wide range of methods that people have looked at over the last decade or so. I'm not going to get into the categorization of different explainability methods, but there are very nice tutorials and even books online that you can learn from if you're interested. But the part that I'd like to get into is a significant part of existing work in explainability and interpretability has been on explaining the decision of a trained model as a post hoc effort. Right? So that's been, if you look at popular methods like LIME, SHAB, GRACAM, LRP, etc., all of these are post hoc methods where you interpret a model trained a priori And this was well worth it because it was easy to integrate with what already existed. You didn't need to reinvent models from scratch, and it had its purpose over the last few years. But we're perhaps at a time where we now need to reimagine what explainability means. So far, the approach has been to consider a neural network and then add an explanation module at the end post facto to explain what the model used to predict. But what I'd like to advocate is for going towards an approach where you have the explanation module itself as part of the learning process itself. And that's the work that I'd like to talk about in the continual learning context. But before I get to the work itself, I'd like to give the bigger picture here is you could view this approach of learning to be going from learning via prediction to learning via explanation, right? I hope all of you will agree that our focus in machine learning has been on learning via prediction. But how do you learn via explanation is what we typically expect kids to do, right? So how do you teach machines to do something like this is what we'd like to advocate for in this work. So just to explain what this means, this is just one way of looking at it. But if you have an image and you gave it to a machine learning model and the model called it a cat, that's the way we typically train machine learning models. Can we rather go beyond this to an approach where you give the same image, you give it to a machine learning model now. Now, instead of predicting directly, the model now looks at the pointy ears, looks at the whiskers, looks at the beady eyes, the four legs, the furry coat, gets all those intermediate semantics, and now reasons and says it's a cat because of this, and this, right? So this is what I call as learning via explanation. And this perhaps is just one way of doing it. I'm not just going to claim that this is the only way of doing it. And beyond being able to give explanations, I think this has a fundamental advantage where reliability and robustness come along for free. Because reliability, because you can explain your decision, and robustness, because you cannot change a few pixels now and expect all the intermediate semantics to change. Maybe the output could, but not all the intermediate semantics. That's what we'd like to advocate for here. And the work that I want to get into more detail now is this work that we recently did, which is on continual learning with multimodal concepts, where we'd like to go towards an explainable continual learning framework. Okay, that's the overall idea. It's exploratory. It's joint work with students, Susmit, Siddharth, and Deepika at this, who helped with this work. So far, the fields of continual learning and interpretability have been studied separately, right? But the synergies of these two directions have largely been unexplored, and that's what we like to tap on in this particular work. So we view interpretability through the lens of high-level abstract concepts. This may not be the only way to achieve interpretability, but that's the approach we have chosen in this particular work. And if you see this overall graphic here, this is what we're trying to address, where typically when you talk about continual learning, you have your images and you get the classes for those images in a broad sense. But when you now bring in concepts, which I broadly say capture intermediate semantics, right? So now it's possible that in a task 1 of continual learning, you have a certain kind of intermediate semantics that's provided to you. When you go to task 2, you have a whole new set of images and classes. Now that could also result in a new set of intermediate semantics too, right? So that there could be a new set of concepts which were not there in task 1 that comes into task 2. And this combination can be a complex web of relationships between data, concepts, and classes now. Historically, continual learning only looked at data and labels, but now there's an intermediate semantic into play. And now the web between these can become far more complex than just data and labels. So we also introduced this notion of concept class relationship forgetting, where we show that beyond the traditional catastrophic forgetting we talk about, where the model can forget the labels, the model in this scenario can also forget the relationship between concepts and classes, right? It's not just class and data. The relationship between concepts and classes can also get forgotten because you may not have access to the concepts from previous tasks. Okay, that's what we try to do here. So what are the questions here? Can these kinds of relationships be learned across experiences in continual learning? And once learned, how can you preserve them across experiences is the second question. So our objectives here is to incorporate.
It's taking it from the
great.
it seems to be.
Okay, great. The objectives is to incorporate newer concepts and classes in a scalable manner without any increase in training parameters. I'll come to that in a moment. Integrate concept-based interpretability without any explicit annotation or creation of new data sets. Okay, that's something that we laid down for ourselves, that we don't want to now be creating a newer generation of data sets based on these concepts. How do you leverage what already exists? And we want to learn these concept class relationships across experiences while preserving existing ones. Okay, that's our overall objective. And this is the overall framework that we propose. I will take some time and walk you through this. So on the left, what you see is the data setup that we have. So you have your experience one, where you have a set of images, a set of classes, and also now a set of concepts. Okay, that's the new dimension compared to traditional continual learning. And when you go to episode 2 or experience 2, you again have a new set of images, a new set of classes, and a new set of concepts. Plus, you have some replay buffer that comes from previous classes, concepts, classes, and data, and so on and so forth. So on the right, what you see is our overall architecture, and our approach to this was to try to make it as contemporary as possible, use as many contemporary frameworks as possible. So we send the images through a Flava image encoder to get the image embeddings. We send the concepts and your class labels through a BERT embedding to get the text encoding. And both of these together, so this middle one is your concept encoder, and this one here is your class label encoder. So both of these, the image embeddings and your text embeddings, concept text embeddings, together go through what we call a multimodal encoder, which is a very simple transformer with 2 blocks. That's what we use. That's what we find is good enough. And you get the output embeddings of each of your input tokens at the output of the transformer. And now what you see is you have a few different losses. I'll talk about each of these losses on the next slide. But these concept embeddings that you get here go through what we call as concept neurons to do a concept classification to understand what that concept stood for. And we also now use our concept neurons with the class label embeddings using a cosine similarity classifier to say what class your final output was. Right? So that's the overall framework here. Let me talk about the loss functions and what were some key ideas here. We used 3 kinds of loss functions: a weighted binary cross entropy loss, where you can see the weighting is on the number of inactive concepts and the active concepts in each mini batch or data that you get. The reason we needed to do this is if you don't do this, you could end up having a very biased cross entropy loss, which could be biased towards even inactive concepts. We wanted to ensure that the cross entropy loss penalizes the active concepts for a particular label. You have the ground truth for the concept, so you can penalize it. So that's why we have this weighted binary cross entropy loss. We also have a concept grounding loss where the output concept embedding tokens of your transformer is matched with the concept text embeddings to ensure that they both align with each other, which means you're trying to maintain the semantics of your concept embeddings with what is known out of the text embeddings. And finally, we have a parameter-free classification here, and that's what helps us be able to scale up in the number of concepts without any increase in the number of training parameters. Right? So what we have here is just a simple dot product between your concept embeddings and your text embeddings. No weights involved. And having no weights is what helps us be scalable in terms of the number of concepts across experiences without adding any particular heads there. Right? So that's the overall architecture that we have. So the key ideas here are an extensible concept set. This allows us to extend any number of concept sets without any increase in parameters across experiences in continual learning. We perform a similarity-based classification, and our experience replay includes your data, concepts, and your classes too. Right? So that's how we use the experience replay. And how do we get the interpretability out of this? So given an image and a set of available concepts, we predict which concepts are present or absent in the input image using our concept neurons in the architecture. So that helps us tell which concept was active in a given image. And the set of input concepts that you provide to the transformer contains all concepts seen until a particular experience. Right? So obviously, the reason why this kind of an approach is scalable is because of the sequential learning of transformers, which means as newer and newer concepts come into your continual learning framework, the length of your input tokens to your transformer can increase, but then it doesn't matter because you're anyway going to use a transformer that's going to give you equivalent number of embeddings on your output, and you can use that to get your concept neurons. That's the overall idea. And with this, we compare with a few different methods. There are not too many methods in this direction. To the best of our knowledge, there's just one paper which is somewhat similar, not exactly the same, but perhaps this is one of the early efforts on trying to bring interpretability into continual learning intrinsically. That's what we were trying to do here. But we try to adapt some of the existing concept-based learning methods to a continual format, and we were trying to compare them on standard continual learning metrics like final average accuracy and the average forgetting. And we see that we do significantly better than many of these methods. One of the metrics that we actually introduce a few different metrics here, but I'll talk about one of them at least. One of the metrics that we introduce to study, because we now have a new variable that we are introducing, the notion of concepts in continual learning. So we needed new metrics to study how well this is being learned. So we introduced the notion of an active concept ratio, which studies the relevance of concepts to a classes in a particular experience. Right? And what you see here are three different methods for a standard concept bottleneck model, a label-free concept bottleneck model adapted to continual learning, and our approach. And what you see here along the diagonal is that our method picks the concepts that have arrived in a particular experience as the most required for the classes that come in that experience, while you can see that the other methods are heavily biased towards certain concepts because they were not explicitly trained for such an approach. We also show that using such an approach, using attention visualization of the heads inside the transformers, you can now get more precise localization of concepts too. Right? So beyond just visualization at a class level, which we know methods like GradCam and other things can do, you can also now use the attention heads to visualize concepts. You can now say that I'm calling this a cat because see here, this is where the pointy here is. See here, this is where the beady eyes are, so on and so forth. Right? So that we do using the attention head visualization. So this also gives us some amount of interpretability. And we also show that you could now play with this by intervening on the concepts. So here is an example where the model classified something wrongly. So it took an image of a Komodo dragon and called it a sea turtle. And when we examined the concepts that got activated for that classification, we identified one of the concepts to be wrong. And when we switched that concept, we got the classification correct from the same model. Okay, this just showed that there was an explicit concept-class relationship being learned by the model as part of this entire framework. Okay. Just a quick summary of that. This was an exploratory attempt to make continual learning inherently interpretable with some new metrics, and hopefully we hope that this will spark more such efforts in this direction. This also happens to be one of the posters that we submitted to the CLVISION workshop. So if you're interested, please do stop by, and happy to chat more with you on that. And the first author wanted me to put this down, that he is looking for PhD positions. If anybody's looking, he's available for PhD positions next year. He's a master's student currently. Okay, in the remaining few minutes, let me also talk about the other work that I want to talk about. And let me again reiterate, my purpose was to bring in a couple of newer dimensions to continual learning beyond the standard ones that are discussed. That was the purpose of this particular talk. And the second work is called Continual Privacy-Aware Personalization of Human Actions with Prompt Tuning. Right? So I personally think this is an interesting take at continual learning too, potentially something that could be very, very practical and real world. This is joint work with Prachi, Joseph, Shugao, and Fernando, joint work with CMU and Meta Reality Labs. So all of us know that the traditional XR, VR devices that are shipped out today go out with a predefined set of gestures, right, or actions. And that's what everyone plays with on these games or whatever software that you interact with. The question that we try to ask here is, what if a user wanted to add newer gestures to their devices over time, right? Beyond the pre-shipped gestures, if you wanted to add newer gestures to these devices, how do you go about it, right? We have a few options here. One is you can train separate models every time a new user gesture is added. Two, a user could query the service provider or the hardware provider to add this gesture. Or three, which could be to use continual learning to train a single model, to ship it out, and make it easy for the model to learn on the fly with newer user gestures. And clearly, we picked three to see how we could leverage continual learning for such a task. And the key objectives for us here is to train a single model that continually extends to newer gestures over time. It should ideally easily adapt to new knowledge. It should not forget the old default gesture classes. You do want them to be in the bank too. You don't want them to change. But at the same time, you cannot access older data due to privacy considerations, right? So I think there are tremendous issues around exactly these kinds of devices in the legal space at this point in time. So we definitely cannot access the past data here while updating your model. So this is the overall graphic. You could say that you have your base trained model, which is locked now. You cannot access the data that comes from that. But each user may now want to add newer gestures to this model over time, and they may only provide few samples to do this. So the technical challenges here turn out to be continual learning of new human actions, few shot learning, where the user may not provide you too many samples to update your model in newer experiences, and you have to be privacy aware with absolutely zero knowledge of past users' data, no replay allowed, right? So you cannot replay from your past tasks. That's what we were trying to work with here. So the approach that we took for this to solve this problem was a prompt offset tuning approach, where the main action classification model looks somewhat like this. We chose a 3D skeleton-based approach to handle privacy issues. So because skeleton by itself mitigates the privacy issues compared to vision to image data, it goes through an input layer, then you have an input feature embedding, then it goes through a feature extractor, your classifier, your standard action prediction. Okay, the base architecture is pretty much standard to any action or gesture classification. But what we add here are these prompt offsets to each time step. So some of the things we do differently here is that we depart from standard continual prompt tuning works. There have been works such as learning to prompt for continual learning in the last couple of years. We had to do something different from them because most of these existing works, when they do prompt tuning, assume access to a large pre-trained model. Unfortunately, when you deal with skeletal data, you don't have access to such foundation models as things stand now. And action recognition are typically modeled using graph neural networks and not studied for the non-transformer kinds of architectures. Okay. So that's what we were working with, and this is the overall architecture that we come up with. So what you see on the right is what you saw on the previous slide. That's our overall pipeline. But the prompt offsets that we add here goes through a prompt selection mechanism. So we have your input data, T frames of data, temporal, spatio-temporal data, and it goes through the feature extractor, and we also get a query feature out of it, and a bunch of learnable key features. And using a query key matching, using an attention mechanism, we now use that to index and select a set of prompts from a prompt pool memory. So you have a memory of prompt embeddings, and we now select a certain set of prompts, which we add to the given input for every task to be able to predict that particular data better. Okay. It's a traditional prompt tuning kind of an approach. The losses that we do beyond the standard losses that we have are a cross-entropy loss on a user's new data and a query key clustering loss to be able to match the query key better. So our results here is we show results on a couple of data sets, a 3D activity recognition benchmark and a 3D hand gesture recognition benchmark. So since we were perhaps the early effort to do continual learning in such a task, we had to set up these data sets for a continual learning benchmark, where the 60 classes in the NTU RGBD plus dataset is split into 40 plus 5 plus 5 plus 5 plus 5. And the Shrek dataset is split into 8 plus 2 plus 2 plus 2 for different experiences. Okay, that's what we do here. And we compare our method across many approaches, including just using the feature extractor itself. The FT stands for fine-tuning the entire model, so on and so forth. And we show that our approach significantly improves performance on both the old classes as well as the new classes by a significant amount, as you can see here, by about 10% or 20%. This is also figuratively shown here in terms of the stability plasticity trade-off, where our method here is the line on the top, where we get the least amount of forgetting in different settings, old classes, new classes, harmonic accuracy, and the average accuracy. We also show similar results on the hand gesture recognition task on the Shrek dataset. And we also study this from the visualization of the prompts on the activity recognition task, where we see that when we use our approach, the prompts get evenly spread across the prompt pool in different tasks over time. I know I only have a few minutes left. I wanted to leave some time for discussions. I'll wind up in a couple of minutes. The reason I wanted to present this work was beyond these early explorations that you just saw on the previous slide. I think the space of continual personalization can actually be an umbrella of problems, right? Beyond what we just saw right now. It's possible that a user may say that I don't wave my hand the way Meta shipped out a particular device. I wave my hand differently. I come from a different culture. I'd like to wave my hand differently. How can I update that gesture on my device the way I'd like to go about it, right? So this is continual learning, but now I want to go change the data for a previous class. I may also want to add new gestures over time. And a third direction is also inter-user personalization. So now I may have a family of 5 people using my XR/VR device. How do I now have different users' gestures be added to the same device, maybe as separate tracks, right? Each user may add different gestures. A different user may want to start from a base model and add a different series of gestures over time. These provide an umbrella of problems to solve in the continual learning context, which we'd like to call as continual personalization in the user setting. With that, I'll stop with just a summary and a few takeaways. A lot of open questions. I think newer settings such as explainability, privacy awareness, or personalization bring about newer challenges for continual learning, which are, I think, worth exploring for newer frontiers. And when you look at the different settings that we all work with, right? So I think even Mark had this in his slide. We talk about continual learning, test time adaptation, domain adaptation, zero shot, few shot, transfer learning. How do you unify all of this? Obviously, when we talk about the grand goal being AGI, we want a single system that performs all of this, then different systems performing each of these tasks to different benchmarks. How do you unify all of this still remains an open question. I also think that begs the contradictory question or the counter question, which is, do you really need general purpose systems for all tasks? Or when do you need general purpose systems? And when do you need narrow models where perhaps continual learning could be more useful in practice? Especially, I think it's a good debate to have in the context of foundation models. And an obvious question with all of this is, how do we develop benchmarks for these kinds of settings where we respect and use foundation models the way we should use, but still elicit interesting problems to solve? I think I'll stop here. Hopefully this was of some use. Thank you again for being here and the invite. I'll stop here.
So we have a microphone here. Do we have some questions from the audience?
Thank you for the great presentation. Very informative. I had a question about the first part, the first paper that you showed, that we are using concepts to classify better for the given inputs. And it's all based on supervised learning, right? So what were the, like, how did you have to label the images again with a lot of concepts, and what were the regulations around like how to label the concepts apart from just the final classes? Labeling itself takes a lot of times, and if the humans are to give different concepts, like what are the regulations should be given to them to label them?
Absolutely. I think that's an important question. I think I kind of glazed over it. So in this particular work, we use LLMs to do that. The nice thing about concepts is you need it only once for a class label. You don't need it for every sample, right? So you only need it once for a class label. I think there could be more interesting nuances when you go deeper in this. You could always say that certain images don't capture all concepts, right? You may only see a cat from a profile view, for instance, right? So there are more interesting nuances to look at. But in this particular work, we just got that from LLMs directly to go in. There has been some earlier work in concept bottleneck networks to do something like this. So we followed them and just queried LLMs. And it's not too much effort because you're doing it at a class label level. That's what we did. Sure.
Maybe you can come to the front if you want to ask the. Yeah, but it's for the Zoom. Yes.
Just a quick follow-up question on that. So when you use class tables to create concepts using LLMs, how can you make sure that the text LLM generated is actually describing what's there in the photo? Because one class may have different types of photos, we can have different types of concepts, right?
Correct.
Same object, but different.
Absolutely. So currently we query the LLM just based on the class label text, no images involved. No images involved in the LLMs, right? So at this point, we are trusting the LLMs. And for this work, we just manually curate it because it's not too hard. You have, say, 100 labels or 300 labels, you can manually curate it to get what you want. But I do agree it's a challenge going forward. And I do think questions around what if your labeling noise, your concept labeling is noisy, just like how we talk about class labeling being noisy, partial label learning, all of that can also spill over to concepts. I do think there is a lot of discussion to be had, but in this particular work, we trust LLMs, right? So we assume, but we did manually curate what we could.
Maybe one last question.
And my question is rather general. And so before LLMs come, I remember in incremental learning, people dealing with a lot of challenges like concept drift, like forgetting, like stability, plasticity, balance. But after LLMs came and after the boosted generative models, it seemed that it was the end of continual learning because they didn't have any of these challenges we had with distribution with any useless. How do you think the direction of the continual learning is going to shift with the existence of it?
I know there's a question for the panel discussion in the afternoon, so I'm sure
Very good question.
I'm sure we'll talk more, but maybe just some initial thoughts on this. I think it's a difficult question, and I do think the entire community is grappling with this as to what do all of these settings like few shot, zero shot, continual, what do they all mean when foundation models can pretty much do all of this off the shelf, right? So I do think I feel the jury is not yet out is what I feel. I think we still don't know exactly what it stands. But some initial thoughts on trying to see, I do see, I think RAG, when you use RAG, I think it's a different conversation to have. But I do see now as LLMs are coming into mainstream search, right? We do see LLMs coming into mainstream search on your basic Google Windows or Bing Windows or so on and so forth. I think there is a need for getting current information. Right? You no more can be 6 months old in terms of the data that you've trained on. Right? I think that is becoming an important requirement as LLMs come into mainstream search. So I do think there is a space there for continual learning to be used. Currently, these models are trained from scratch once in every few months, right? But I think that may not be enough when you want your information to be current. I do see that to be one important discussion perhaps to have in the panel itself. I still think it's an open point for discussion. The other thing I also wanted to mention, which was one of the open questions I had, is I'm not sure if general purpose foundation models are the solution to all problems. I still think that there will be many applications around the world which are niche, which probably require things to be small and specific applications where I do think, I think when we talk about LLMs and foundation models, we're always talking about web scale problems. Right? So that's the problem we're talking about, the web scale. But then there are many other problems in a local neighborhood or a local hospital or in a local farm or things like that, which may not need those web scale kind of problems, right? It could also be, these kinds of issues could also be governed by security issues. I still feel in those kinds of narrow models, continual learning has a role to play. That's probably one way of seeing it. So I think it has a role to play even in the foundation model space and even in the narrow AI space, if I can call it so. So that's my current thoughts, but I'm quite sure we'll discuss this more in the afternoon.
Please thank our speaker. We will move on to the next one. Also, thanks to Suzmit, your student was answering questions in the chat. Ava,
Yes, I'm here.
are you ready?
Yeah, I am ready. Can I share my screen? It doesn't allow me to do that.
Wait a second, trying to figure out if we can have an audio output.
Let me see. Can you see my screen now?
Is it what? Yeah, that's it. This is on. It should be. Ava, can you try talking?
Yeah.
Share microphone is it?
Yeah. I can talk, and I hope you can see my screen too.
And if we remove this. No, it's the Epson one. No.
Can you hear me?
The speaker on Zoom.
On Zoom here. Are you right? Here?
Yeah, can you hear me?
This one.
Can you see me?
Yes, we can hear you. Thank you.
You can hear me? That's great. What about see? Can you see my screen?
Yes. Wait, where is the full screen here? Am I blind? Okay. I mean, you can still follow it, I guess, no? Yeah. Okay. Okay, our next speaker is Ava Siegelman. She's a senior faculty at the University of Massachusetts, and as beneath, she's been doing a lot of continual learning and neuro-inspired research for a long time, right?
Yeah.
So today we will have Ava talk about lifelong learning AI at the edge. Please, Ava, the floor is yours.
Okay, thank you very much. Thank you for inviting me. And I really enjoyed so much the first talk. So I think the whole day is going to be fantastic. So just for the fun beginning of that, we all see how human capabilities we can see in games and, you know, maybe even chat, some people say, but we still have this issue of when we take the AI in unstructured environment, we're getting stuck. And I think that the explanation of many of us here will be that, you know, there's the first wave AI with the rule-based and programs that we told the program what to do. It didn't generalize well. So we moved to neural networks that we collected data set for them, but there's something in common. So both of them, the classical setup is that they're frozen, and it's still the majority of what we have today. And I think about it in a way that we improve capabilities in training, but then we can fail if something comes that you're not expected. So this type of AI that is not part of this workshop, I call we know it all in advance. And it's kind of like the gorilla kind of showing on itself, we know it all in advance. And, you know, people talking about artificial general intelligence and all kind of things. I don't think that there is any chance for that without continual learning or lifelong learning. So we have promises versus reality for many years. And, you know, one suggestion is just to have even greater data collection or even larger clouds, even more energy. Not enough that we already spend so much energy for the training in advance. Maybe we need to pollute the world even more. So this is one option. And the other option is to rethink AI as more like what we see in nature. So, you know, we kind of understand that organisms can be thought of as following programs. And it's not just an empty words. It actually helps us because then we can translate mechanisms from biology to advanced AI, which is something that, you know, in my years, I've seen a lot of advancement really coming from biology to AI. And we can also study and try to understand biological systems property by taking some properties into AI and see what kind of intelligence it's gives. So because of this organism can be thought of following programs, many people use the Turing machine model because it's that common in theory of computation. And they've been modeling cells and brains and bacteria behavior. But as I say, Turing machine is insufficient to describe nature. And if we insist and get stuck to that, it really limits our AI, and it really keeps our AI too energy hungry, which is anti-nature type of computing. So just kind of for the one of us that didn't come directly from computer science. So Turing in 1936, he was thinking about what they called human calculators. These were the ladies who were sitting in the back offices of the bank or other places. They're, multiplying vectors and matrices, and they're doing whatever we call today calculator. These were the human calculators. And Turing wanted to explain how the human calculators are doing that. And what he said is you don't need to have new hardware, a new brain every time. You just teach them one thing, let's say how to multiply matrices. Once you loaded this program of multiplying matrices, you can give any two matrices, and with a little bit of scrap tape, a little bit of scratch paper, you'll be able to provide the output. So you say, these human calculators, you just load the program and that's it. And this was a huge thing in the evolution of computers, because it's really proof of existence for general purpose computer. We just need to load the program and it does what we need. There is an issue here though, that all this calculation has the loadable program, and this is the basis of Turing. So if you want to think what Turing animals are, so I think that we can think about Turing animals to have these animals that have huge brain encoding of what maybe we'll be able to do. And if we don't get what we need, we didn't have what to do in something else, then these animals will not stay to procreate. And the Turing AI is kind of like the older type of AI, I think, where we must load the program or train in advance. And even if we are not really happy and we see that there are mistakes, we're not really updating anything. So the real holy grail of AI is this adaptive intelligence, where we don't want to stay with the pre-programs that we're giving in advance. We want to kind of update and make surprises and show flexibility and robustness. So if we think about the foundation of that, of strong computing, so we understand animal survival is based on this adaptivity. People's health is based on the ability to learn. So I have a question to everybody here. Who said electronic computers are intended to carry out any definite rule of thumb process which could have been done by human operator working in a disciplined but unintelligent manner? Who dares to say that computers are not intelligent? So that's the answer. This is Turing in 1950. So if you want to start thinking about computational model that allows us to have adaptivity, allows us to have randomness, allows us to have approximation, a good model for that is suggested was the analog recurrent neural network, that it's really kind of a parametric type of computational model. And I'll show you in a second why we need it. But in general, if we have the Turing model on one side, there's actually a whole hierarchy of models above it, taking us up to some ceiling that we'll call it the Super-Turing model. And there are many ways to go from Turing up all the way to the Super-Turing. One is that the Turing, we can think of the pre-program, and once we have lifelong evolution of the program as we go, this is already upper there. Or even if we don't program, but we have huge brain, instead of just discrete, we have these real numbers, kind of like the real world that have the actual physics there. Or we can go from deterministic to some kinds of randomness or asynchronous. And I think that the main way that I like to think about the difference between Turing machine and the Super-Turing, I think at every moment of time, if you look at animal, even humans, we're following a program. So we're following a Turing machine. But in between these, we update, we learn more, we do more, we experience more, and we update the Turing machine. So this process of learning and computing kind of going together this is kind of like the way of thinking of a Super-Turing model. And the way that we are on the hierarchy can be defined as the amount of information and the time that we take information from the outside or context, or, you know, what was mentioned in the previous talk as these concepts. So if you can kind of take them in, it kind of fast and good. We're higher in, if we take them in just a little bit, then we're a little bit more than Turing. And if we cannot really take more information to update our program, to update our neural network, then we're still in the Turing. So if we have, you know, neural network that we always train in advance is Turing. So just kind of to give the credit to Turing that suggested that there will be machines that will be like more like humans. And he suggested already in 48 not to listen to people that said that everything will have to remain in his Turing model. I like the first two of them. He has 10. One he called the head in the sand, like we cannot allow such a disaster. A machine that evolves, a machine that learns, will take over the world, will all die. So you say, okay, that's a hand in the sand. It's not a question of technology will be there, it's fear. And I also like what he said is Lady Lovelace's objection, which is say, you know, currently machines are doing what they're told. He said, that's fine, but maybe in the future they will not. So he actually was talking and starting this way of thinking of something that is kind of more complex. So the way we can think of lifelong learning machine, or the way that I kind of introduced it in DARPA at the time, was that instead of being here, it's a machine that kind of keep open. And as it sees that something is new or we're not predicting well, I like also the notion of just predicting well, maybe also explaining well, taking from the previous talk, then we can continue and update it. And in general, for all continual learning that you guys are working on, just the fact that we can update as you go, it means that we don't need so much data at the beginning. So we don't need exhaustive training set. We don't need a huge energy for training in advance. And we have a long life cycle. So we all kind of benefit from there. So I was the PM at DARPA that introduced the lifelong learning machine, and we worked with people from many countries. And, you know, during these years, I think that what we found most useful were the replays and the self-directed learning. And there is a paper on that, you know, the group was putting together. And you all know this type of work, and I'm not going to teach us catastrophic forgetting. That's how I started the program there originally. The interesting part is that, at least the way that I view the lifelong learning is, do you really need to put together things? And you really need to have online streaming. And I'll explain to you in a moment why I think these are really needed. And I like, you know, the previous idea for call it organic, but when we talk about lifelong learning, which enable on-device learning. So first of all, we have the streaming, so we get this natural data, so we don't have class at a time. But then as we go to mode of learning, we have to have online and offline. And the reason that offline consolidation, where we can have the replay or rehearsal, if you want to call it, and the self-directed learning is not really sufficient, because many times there is something that has to do with safety or with importance that I want to say one time and have it done immediately. So there are things that have to happen right away. And it's okay to have, you know, the big learning once in a while, but we need to have updates all the time. And the third point that I will be actually talking now is, if we have on-device learning, we want it to be far from the cloud. So we want it to be edge AI with low power and low size. So the question is how we get that one. I think we have some knowledge already about streaming, sometimes actually much easier than learning one class at a time. I will talk about online and I will talk about edge. So the reason that I showed Super-Turing there, I was working on Super-Turing in earlier years, and I really left it. I kind of considered it to be more like theoretical computer science, and I come from theory, I liked it, but as I moved to neuroscience, I thought it's not that relevant. But I kind of later realized when I was studying human memory that features that we see in Super-Turing are actually telling us how to make AI better. So one feature that I want to show today is what we call linear precision suffices. Like if you have a neural network with great precision and you have another neural network with small precision, it's as small as the number of steps that you're going to use it to get reply to your query. So there is no way actually to separate between the two. So up to k-step of computation, you would never know if you use a very detailed neural network or one that has only just a little bit of bits. And it means, it actually has some meaning. One is it means to us that we can compute chaotic classes in continual learning and lifelong learning in Super-Turing. And the other one is that the process of learning and computing is actually feasible. And what I'm taking now is this proof into a feature that we'll call it use only as much resource as you need. And I want to show you that when we do that, we actually get lifelong learning, which is very saving in power and in everything else. So I'll show you just very fast each of these. So the first I want just to say about how do we do online and why is it so important for us? So I think there are a few ideas for how to do online learning. The two that I like were the one that Hinton had and the one that my group had. We actually had it before, and I think it still does better. And the idea is that instead of having the back propagation where we have to put the input and to wait until it comes back, when we're waiting, we're really missing more data that is coming, so we cannot really doing it online. And we kind of usually decide the number of possible classes. We want something that we can get in, and as we compute, if we need, we also update, and also we can update and add more ideas. So the idea is that instead of having input here and label here and kind of learning to change the weight so that the input will be transformed into the arbitrary label. So what we do is we start with the input and the label at the same end, and we start taking them together until they come together. So it's not just the input will have to come to the output, they will both kind of move to each other and meet somewhere. And as they go forward, if we see that they're too far from each other, we make very localized update. So it's actually very easy algorithm. It's funny how it's easy. We take the labels, whatever way to transfer them to the input dimension, we can just add zeros or whatever, just to have the same dimension. And we put them both in a twin network because it's the same space. And really at every stage, we just compare what we get here and here. And if it's too far, we update these weights. But anyway, we continue forward. We never propagate. If this is too far, we just update the entrance to here. So that's kind of the picture. If this is too far, we just update here. And we continue going forward and kind of that way. So all in all, we get, oops, I went to the wrong direction. Okay, so we kind of go step by step. And we can think about it as the label getting in the input space closer to where the input coming from. And it's really perfect for on-device AI because we don't need to freeze. We can have as many labels because it's in the input space. We don't actually need local memories of the neurons to remember what they had output because we don't have to repeat, wait until something comes back. It's just kind of a forward process. So this is not as good as back propagation, but it does a lot of things. And I started using this in order to do the online learning when I do the replay and the full consolidation once in a while. So this is one way. The other one, this is with Devder and Francesca and with Terry Sejnowski. And here it's an idea how we can take this idea of using minimal resource to improve on real-time and very low energy control. So the idea is that in current reinforcement learning, the only reason that it succeeds is because of many, many, many steps. If we had only as few steps as human is doing, it will not be doing very well. So instead of having regular reinforcement learning, we're actually going to have temporally layered. So there are lazy networks, and there is one quick network. And the lazy networks have also switch network that switch between the two. And this is very, very bio-inspired. And what is nice about it, I think, is the results. And I want to show you. So here we compare between TD3, between a algorithm that is called temporal. Temporal has the notion that it can repeat the same behavior many times. And because of that, it's like doing the same sequence many times. So if you just need to repeat, you don't need to calculate again. And what I want to say is what is really special in this program is that not only it's doing, return well, but it's doing the jerk well. So the jerk, it means that if you had the robot outside, it will take very little energy, also little energy to calculate, and low energy to decision. So we tried it in a few things. We just kind of sent to publication. I think that's what I find interesting. And I don't know why, it gives much more balanced walking than state of the art. I don't fully understand. We don't fully understand. This is a work in progress that we currently are doing. Oops. So we add some more sequence learning, and in general, what it does, it gives us about the same result, about the same accuracy, but with much, much lower energy. And the reason, the whole trick here, is that we use very slow steps, and only when needed, we take very fast step. So if you think about it, if I drive to work and I know the way by heart, I usually don't think. Only if it's, snowy or there's tons of traffic, I need my whole focus. So most of the time, I use very, very little focus, very little computation, and only when needed, I use the quick. So the quick is kind of like what we have in regular RL, but practically we can work a lot with slow. So there is another trick here, which is change the weights so that the weights actually are not anymore a number, scalar, but rather their function. So we get with the same neural network kind of like a behavior, and we use it for environment which are not naturally circular. And by doing that, it can manage, if it's kind of a circular like environment, to use this feature that we learned that it's kind of circular, doesn't have to be perfect, to be able to use very, very small models. And so if I want to think about the temporal versus static, in regular neural network, if you want to have small neural network, we usually train very large one, and then we can prune, because we don't know how to take a small one and learn it. With a temporal, it's actually the opposite way. We start from small, and if we need, we add a little bit more. So it's kind of a different way of saving, of kind of using little resource as we want. I want to say just one more thing before I end about the Super-Turing, and this is work with Jeremy Cabeza. It's actually older work, but I find it kind of to have a different meaning. Once we moved Super-Turing into AI, it has all different meaning. So if you take this, what is called interactive computer paradigm, so it's not like input, output, and every time you have to remove memory in the regular paradigm. So here you give like input as a sequence, and you start giving output. It's kind of like animal that is not supposed every time to remove its memory, that's the meaning of stopping and doing again. So in general, you have Aleph 0, many Turing computing, or many fixed neural network. Aleph 0 is kind of like the number of integers, the infinite number of integers. The analog recurrent neural network, or the Super-Turing, will have exponential number of them. We'll have 2 to the Aleph 0. Different capabilities. So it means that if you want to have like a test, so the Turing test is really comparing between Aleph 0 and human capabilities, and the Super-Turing test is what we do to separate between an exponential expressivity and human, and that's kind of much harder. We kind of start working on that, and if you guys want to join us, it will be fantastic. I kind of believe at that stage of my life that even with lifelong or continual learning, there is some limit that we cannot pass. And this is this 2 to the Aleph 0, or this is like what we call the complete Super-Turing. And there is some math to there, why I think that there is a limit there, that it's not far from everything. And just to summarize for intelligent edge computing, to suggest that maybe AI in a few years will be considered intelligence if it has these Super-Turing capabilities that comes to lifelong learning, going to continual learning. And just to say, we're in the first steps. We have just a few papers that we've written, and we're all under submissions now. Everything that I talk today is under submission. Nothing is still there. So if you want to join us, if you're interested in how to do the lifelong learning on the edge, I'd be very happy. And thank you very much.
Thank you, Hava. Do you hear me well?
Yeah.
Okay. Do you hear Gianluca also?
You hear this?
No? Okay, maybe then we'll repeat the question. Okay. Is there any question from the audience? Okay. I have one question from some of the analogies that you've been talking about in more natural systems. What also happens is that plasticity goes down, right? Like as you grow older, let's say, like stability gets a more prominent factor in the plasticity stability balance, right? How do you think this relates for moving from more natural beings, let's say, to when going to machines, basically? Yeah. Do we also have to try to embed into some of the lifelong learning systems that we do kind of a stability-driven over time system that will also put a limit to the capabilities of what you can learn, or what are your thoughts on this?
Yeah, so I think that, for animals or for us, that we kind of get older and learn less well, or maybe we have so much in our brain that we want to keep it and not get confused, so we're not open ourselves to learning more. So there can be like different reasons for why we see that. It can be something that we kind of push ourselves to do, or there can be degradation. So I think that based on the view, we can think what we want in AI. So in general, we don't want an AI that is degraded. As far as I'm concerned, the AI should live for 500 years, and not die 100. On the other hand, there is the point that as you have many concepts, and it's working on that comfortably, you're free to touch it because it's doing something very well. I think that it comes maybe even more in what people are now talking about the AGI. It's not just they want you to do one thing very well, but they want you to do everything very well. So I think that maybe an answer here, and I really like that you brought it, I think maybe an answer here will be to talk about different types of memories. Maybe if we have different types of memories and we can kind of flip or change and put things that are really, really important for us in some kind of memory that is more reliable, and kind of bring it in and adapt a little bit under some constraints. I think that will be probably safer and probably will be more similar to what we say, that as we go, we're more worried about keeping information than about learning new things. I think
Sounds
that
good. Yeah, like integrating context, no?
Yeah. So exactly.
Okay. Thanks a lot. Is there from
That's
the
an
audience?
interesting point. Yeah.
There's a question in the chat.
Let me look at it.
So they say, if you modify the early layers, won't it naturally change input distributions of future layers, necessitating updates in future layers? I guess they were talking about the work where you were mixing the targets of the input, right?
Oh, yeah. Okay. Another interpretation would be that the early layers converge first, following the future layers. Yeah, is this also observed in practice? Yeah, so that's very interesting. So what really happened is that you start with the input and the kind of and the label that becomes part of the input. And what really happened in the input space, because they're becoming closer and it's in the input space, you actually end up having the label not as 0, 1, 0, whatever we had, but as a point in the input that is somewhere in the region of where the images. I mean, we did it only in images. It's kind of, it still needs a lot of work for approval. It kind of become like a centroid of a cluster. But it is true that what happened is, let's say that I start at the beginning, they're very far. So naturally, I will start to update here. And I do the update to this weight as I already continue to the next level. And you're right. So what happened is that maybe in the first there will be more update in the first few layers, and at some point when we look at it, there's almost no update at all in higher. So what happened is that we don't actually need to go through all the depth. We actually can have early decision making. So whenever you have, you can do early exit there, and you still need sometimes more layers for things that are more complex or more close to each other. But things that are repeating and simple, you can go many times in early exits.
Okay, thank you very much, Ava. Maybe we will thank the speaker one more time.
Thank you. I'll stay for the rest.
Okay, and then now we will have our first coffee break, and we will be back. Let me check. At 10:45. So please, I encourage that you go to the poster sessions and chat around with some of the people there. Thank you. Just give me 1 second. I will put this. I think you have the same form like you. You will have to share this. Okay, now it should work. How will you monitor the notes? Monitor the chat?
I can just also log in with a smartphone soon because I think questions is fine enough. If I just check and the rocket chat will let you. So I think all the questions are coming through that.
Can you talk on this? Sure.
Test, test.
Yeah. Okay, so we are back. We have now a talk by Yuan Wang.
Yeah.
He's a postdoc researcher at Tsinghua University, and you basically have an interdisciplinary background with both neuroscience, right, and machine learning, which is something that you will talk about it in your talk.
Yeah.
So please, when you're ready.
Okay.
Welcome.
Yeah.
Thanks for coming.
So good morning, and very happy and thanks for the organizer for inviting me, and thanks everybody for coming here. And very happy to see you all in this workshop. Actually, I started work on continual learning 5 years ago, and at that time I was a neuroscientist working on the biological learning and memory, and especially the biological forgetting. And also at that time I knew the category forgetting problem, and which motivate us to explore if our understanding of neuroscience can improve it. And today I try to present a very special talk that reorganize a lot of our recent work to present that how the biological forgetting can inspire and facilitate continual learning. So I have started with some necessary background here. Okay, yeah. As we all know that the external world is very full of very complex and uncertain changes. And in order to adapt to this dynamics, biological intelligence, like our human being, the learning paradigm is naturally on continual basis that we need to continually accumulate knowledge and acquire new skills and to optimize our decision policy. But this for artificial intelligence systems, the continual learning is still very difficult, which is largely due to the parameter optimization process of the deep neural network, that it needs to update the parameter to learn some task. And if it needs to learn a new task with some changes, it has to override the previous learned parameters. And then you will find the performance will drop very severely. And this phenomenon known as the category forgetting, and it's a major problem of continual learning. And because the continual learning is a very important step for the current AI system to adapt to the real world applications. So they have received very wide attention in recent years. And also they develop a lot of very useful methods and which can be which can be summarized into several major categories. And in particular, very interestingly, their original idea, the motivation is inspired by the corresponding biological strategy. And for example, you can perform the regularization-based method that at an additional penalty in the loss term to a loss function to stabilize the previous knowledge and to prevent overwriting, and especially the weight or synaptic regularization that you can deductively stabilize the old parameters that are important for performing the old task. And this is inspired by the synaptic or weight consolidation or some protection program in the biological network. And the second is architecture-based method that you can assign or split the task-specific subnetwork to prevent their mutual interferences. And this is inspired by the brain modularity or some lateral intubation in the biological network that the activation of the specific neural population can laterally inhibit the irrelevant part to prevent the interference. And the third is the replay-based method that you can replay some old experiences when you learn the new task, such as some representative old train samples, which is also inspired by the biological memory play. So although we have made so much progress, it's still very far away from the human level continual learning ability, because to achieve such a continual lifelong learning and adaptation, there is a lot of real-world challenges remain to be addressed. And also there is because our brain is much more complicated than the current explorations and understanding. So there are a lot of biological mechanism, features, and function to be explored and incorporated into the AI system. So to achieve such a very difficult goal, a very important step is to get a much deeper understanding of the continual learning problem. And then from the perspective of both biological learning and machine learning, and then you can glue them together and to leverage their respective advantages. And even for the key concept, forgetting the major problem of continual learning, it has a much broader concept, function, and mechanism within the biological brain. And this figure will summarize the different form of biological forgetting. And compared with the categorical forgetting, there are two major differences. The first is that, the categorical forgetting is more like a positive or negative event, just like a new distribution come and the old one is forgotten. Such a positive forgetting also happens in the biological network, that the old memory just gradually decay over time. But the biological forgetting can also be actively induced by some molecular signal like the RAG1, which is a particular protein that can initiate a lot of downstream events about forgetting. And such an active induction is along with the learning process, just like the learning begin and also the forgetting begin. And if you block such a molecule signal, then you can see the memory retention will be much stronger. So why the forgetting is actively induced? There are a lot of potential benefits, well-known benefits, such as the flexibility that you can remove some outdated or conflicting information and for better adapting to a new distribution. And also like the generalization that you can remove some too detailed and too specific information, then you can help to abstraction and then adapt some structured knowledge to some similar task. And on the other hand, the category forgetting is more like the overwriting of the network parameters, such a kind of event. But for biological forgetting, in this context, it is generally defined by the behavioral response, just like after you're learning a task very well and you perform it well, but after some time, you just cannot perform it. So you see, you forget it. But it not necessarily means that the old knowledge is removed or eliminated, but it's also possible that you just cannot retrieve it. So if you are provided with a similar context as the environment where you learn the experience, maybe you can recover it again. So such interfered or selective memory retrieval can be seen as an extended understanding of the forgetting problem. And from the context of machine learning, you can see the category forgetting can also have a broader understanding. And in fact, we have done a lot of theoretical study, and we try to identify some critical elements that affect continual learning performance. And here we summarize them into two major aspects. And because we want a model to perform well on a sequence of continual learning tasks, so on the one hand, it needs to properly balance the learning plasticity of the new task and the memory stability of the old task. You should avoid any procedural bias and to perform a proper assignment. And on the other hand, you need to improve the generalizability of the obtained network solution to make it more compatible with the differences of the data distribution. And actually, this element has already been widely discussed in many empirical studies, but we unify them into the same generalization bound that constrain the continual learning errors, and so we derive their correspondence to the continual learning performance. So the key point is that because to address this objective, because our biological brain has already very powerful continual learning ability, so we assume that they have already equipped with a very strong or effective strategy to address this objective from the power of evolution. And we have do a lot of explorations along this direction, and representative work is also published in the last year as a cover paper in the Nature Machine Intelligence. It's a very cool image, right? And in this paper, we tried to establish a computational model of the Drosophila or fruit flies learning system, which is relatively simple, but well understood at the level of both function and the underlying mechanism and anatomy structure. You can see such a learning system have very particular organization, that it have multiple parallel modules that process incremental information in parallel, and in each module, it can regulate the synaptic structure change or the synaptic plasticity to regulate the information over and new in the distribution of such a synapse. Or the synapse is also usually regarded as the parameter that connects the biological neural network, and it can perform active protection of the old knowledge or not old information to prevent the interference and to improve the memory stability of the old task. And it can also perform the active forgetting to remove some outdated, conflicting, and too detailed information, and to improve the learning of the new task, to improve the plasticity, learning plasticity. And also in each module, they have different cell type of the dopamine neuron that convey different kind of super signal, and then to dynamically regulate the learning process of the new task and the forgetting process of the old task. And then they can differentiate into very different functions. And in each module, they have the specific output neuron to summarize their respective advantage together. And then this will have a strong generalizability into very different situation and environments. So inspired by this, we propose a computational model at the level of both synapse and the entire organization. We first discussed each individual module, which can be seen as a neural network, regular network. And we inspired by the tracking of the information in the biological neural network. We also model the distribution of the parameter distribution of the network. It's parameterized by the theta, and which continually learn task A, task B, and so on from their respective training set. And using the use some pointer here, or this one. Okay. Okay. Yeah. Oh, thank you. Yeah. The spatial distribution, and from the view of the Bayesian learning, we can decompose it into two probability. One is the learning of the new task, and the other is the memory of the old task. And the second one has absorbed all information of the old task, and inspired by the actively induced forgetting, we reframe it as the new form of the posterior distribution, and where we incorporate the active forgetting rate beta to selectively eliminate the old data information. And here Z is a normalizer that gives the true probability. And targeting on this new probability, if beta is closer to 0, which means there is no forgetting, and the new form is the same as the original form that remember all information of the old data. And if beta is closer to 1, which means there is 100% forgetting, and then the only p theta remains, there is no additional information. So touching on this new learning objective, we theoretically analyze the two potential benefits of the biological forgetting. The one is the flexibility. We proved that the choosing of the probability of the forgetting rate can indeed eliminate some old data information and improve the probability of learning new tasks well. And for generalization, we proved that the added of the forgetting rate can explicitly optimize our proposed generalization bound. So we can constrain the error of both the old and new tasks. And then we do some derivation, and we get the loss function. The loss function have the two regularization terms on the parameters that corresponding to the function of active protection and active forgetting. And the first one, they have a similar form or as the regular synaptic regularization based method like EWC and others. And the other also have a similar form as the opposite function. The intuitive explanation is that this allows the neural network to perform continual learning with rebalancing with the old and new task optimal solution, and then to strike a explicit balance between them. And very interestingly, in the biological experiment, we also find that the active protection and active forgetting, although they are induced by the respective molecular signal, but finally the downstream event is supposed to regulate the synaptic expansion and renormalization process, which means at the beginning of the learning, the synapse grew a lot of functional connections that absorb different kind of information from the old or the new, and then followed by a pruning process to prune them back to the original amount. But during this process, the information can achieve a well balance between the old and new. So which is very consistent with our loss function and the optimization program. Okay. And then we do the experiment with deep neural network, and you can see compared with the regular regularization-based method that only preserves stability to overcome category forgetting. And on the top of it, the active forgetting can improve the performance a lot of the new task performance and learning plasticity, and therefore to improve the overall performance. And also, you can see when we do the visualization experiments, you can see the active forgetting can indeed eliminate some noise or the background information that is irrelevant to the task and better focus on the object itself. Okay, so that part we focus on each individual module, and we further explore the benefits of its organization that have multiple parallel module, which introduce additional spatial degree of freedom for the adaptive modulation. And in each module, we also incorporated our loss function, because the rebalancing of the old and new task solution is also controlled by the corresponding hyperparameters. So we perform adaptive hyperparameter optimization among this parallel module, and so they have differentiated into different values, just like some module they learn stronger, some of the module they forget stronger, and finally they can have a different expertise in this different scenarios. And we also learn the output weight, which is a fully connected layer to summarize their respective advantages, and finally to have strong generalizability to different situations. Okay, so in order to explicitly demonstrate this adaptive modulation and the differentiation, we construct two extreme conditions where for the different module, we can avoid their innate differences, such as the different random initializations or the different strengths of the dropout. We can first construct a low diversity background where all the modules, they are initially totally the same. And in this case, the adaptive modulation should make them more differentiated, more different to increase the adequate diversity. And also, we can construct a high diversity background where all the modules, they are initially too different. And then the adaptive modulation should make them closer together and to make them more similar to reduce the excessive diversity. And our two adaptive modulation on the forgetting of the old task and the learning of the new task, they have we implement them, and we find that in these two backgrounds they have respective advantage. Some is this better, some is that better in the modulation. And the stronger of the modulation, also the stronger of the performance gain. And if you use the two together, the modulation is strongest and also the performance is the strongest. And after obtaining such a well-differentiated multiple module, we find that they will be more tolerant to the parameter disturbance because they have can complement each other and result in less category forgetting. And that the experiment is essentially to evaluate the loss landscape, the flatness of the loss landscape around the obtained solution, which is also a widely used strategy to evaluate the generalizability of the machine learning model. And then finally, we do a lot of experiments with the different kind of visual classification tasks and the reinforcement learning of the algorithm. And you can see, compared with many similar baseline, we can get a much better performance in continual learning. So after doing this, we have a lot of extension, a lot of paper on the extension, and recent work is also published in this CPR. And in this work, because our previous idea is to cooperate multiple parallel module, so we extend it to the just like to adaptive modulate and cooperate multiple sequential block, such as the convolution block in the ResNet architecture and the self-attention layer in the vision transformer. And we use this idea, make them collaborate, and finally to cope with the more challenging online continuous learning where each task can be only learned for one input. And the first author, Hongwei, will present it here. And I don't talk much about the detail, but he will present it. Okay. Now, we have discussed a lot about the active forgetting, and now we try to move on to discuss the another kind of the selective or the interfered memory retrieval, which is better understood in the more advanced mammalian learning system. So for the mammalian learning system, it is well characterized by the well-known complementary learning system theory. And maybe a lot of you have already been very familiar with it because it has inspired a lot of continual learning work, and especially the memory replay-based method. And in this theory, the memory of the memory of an experience is represented as complementary forms in the two memory systems. And in the hippocampus dependent memory system, the memory tends to be more specific, more detailed and more recent and faster to learn and more supervised. But in the neutronic dependent memory system, and the memory tends to be more generalized or more abstract or more remote or slower to form or more self-supervised. And these two systems, they have very close and dynamic interaction, such as selective memory storage, retrieval, replay, and very intuitively, it's very straightforward that if the two kind of memory they are replayed together, then they can complement and help you to better decision making. And even within the hippocampus, because there are so many specific experiences encoded as a specific form of the memory represented by the particular neural population within it. And such population is activated depending on your external context, right? And then also induced by the corresponding molecular events for the selective activation. And a very interestingly, also a very recent work, we find that the molecule that regulate active forgetting in Drosophila learning system, they regulate such a selective memory retrieval within the hippocampus, which means the same molecule and in the Drosophila active forgetting and then finally achieved by the synaptic expansion renormalization. But in the more advanced mammalian system, it is activate the different population of the neuron. So to exhibit the selective retrieval, this is like a very interesting connection by the power of evolution that the molecule is conserved, but the underlying mechanism we have some differences. So what are the benefits of such selective memory retrieval and memory play for continual learning? I try to explain it with a probability framework of continual learning. Let's consider the neural network parameterized by theta and trained from scratch. It continually learn 2 tasks, and one is each task is a 10-way classification, and finally it should perform the total 20-way classification, and which is a well-known class-synchronous learning setup, right? And we call this goal is a task adaptive prediction (TAP). From the probability of the view of probability, we can decompose it into 2 sub-objectives. And the one is called the within task prediction (WTP), which means you should perform well on each 10-way classification, each task. And this one is relatively easy to address because it's only relevant to the within task data, which is provided by the each incremental task, the training set. But on the other hand, you need to know which 10-way classification to perform, where we call it the task identity inference, especially the task at that time, the TI probability, and it is a 10-way classification. And this one is much more difficult because it depends on the inter-task data, right? So you need to access to the data diffusion of all tasks and you select the task identity. So that's why you need to recover the old task information when you learn the new task, and also that's why the memory play is critical in many continual learning scenarios. And this equation also will formulate the process of selective memory retrieval, because the WTP is represents the memory of a specific experience, and the TI represents the TI represents the selective retrieval of such specific event, right? And but this formulation or this equation cannot explain why such selective retrieval work, because it is equivalent to the one without such a selection, the original one. And actually,
maybe try in 1 minute. Like turn it
okay.
off and then in 1 minute try.
Okay, sure. And actually, this question have troubled us for many years. We try to establish a lot of kind of computational model of the selective memory retrieval, but all the computational model finally they degenerate into this equation. Like although they are learned separately, but the error accumulates, and finally the performance is identical or almost similar to the one without the selective retrieval. And until a very recent work that we start to work on the continual learning with pre-trained model, we understand under which condition such as selective retrieval can bring substantial improvements. And the answer is also very straightforward, is that our brain is essentially a pre-trained model rather than training from scratch. And this conclusion also drawn from a recent paper in the spotlight in the last year's New Rips 23. Yeah. So the original motivation of doing this work is to we will try to explore the benefits of pre-trained knowledge in continual learning. Because at the era of large-scale foundation model, it have greatly facilitated the ability of AI in different aspects, and also including continual learning. And because the pre-trained knowledge not only improve the knowledge transfer for learning each task well, but also it can provide a well-distributed representation, make all the tasks or classes more separable, and therefore to mitigate their mutual interference, and therefore to mitigate casual forgetting of them. But this also introduced an additional challenge, which is the casual forgetting of the pre-trained knowledge itself. Because the pre-trained parameter also need to be updated for adaptation to the downstream task. So they also suffer from the overwriting, and after you turn tuning for many tasks, and finally you find the advantage will gradually lose, and which is also a very important limitation for the application of foundation model in real use. So to address this problem, the state-of-the-art method is you can keep the pre-trained backbone frozen, and to insert some efficient tuning parameters to instruct the pre-trained representation, such as the prompt tuning, prefix tuning, LoRa adapter, such kind of things. And in the context of continual learning for sequentially arriving tasks, such method often involves the construction of the task-specific tuning parameter to absorb the task-specific information from the each incremental data, and also an inference process query function that link to the pre-trained backbone and to infer the appropriate identity of the tuning parameters. So at the test time, it can be inserted into the pre-trained backbone, and then you can collect the corresponding instructive representation, and finally you can collect the final prediction with a single head-off layer that projects the representation to the all potential labels. And such a construction and the inference is very similar to the process of the WTP within task and the TI, the task identity inference. And actually, this method achieves very strong performance under strong supervised pre-training and relatively easy downstream tasks. However, when we perform a more extensive empirical study under more kind of or more realistic but challenging pre-trained checkpoint and the downstream task, we find several very interesting results. The first one is that actually we find that the task identity inference accuracy is very low. It's only around 40% or even worse. That means this method essentially they use an incorrect tuning parameters at the test time. But even though they have such a suboptimal problem, their performance only dropped very moderately. The performance drop around 10%. It dropped some for some extent, but only moderately. And this, with our further exploration, we find it is largely due to that the task identity and inference error are complemented by an additional task adaptive prediction function, which is essentially the single head-off layer. The intuitive explanation is that because the pre-trained representation only requires fine-tuning to converge and to well adapt to the downstream task. So even though they are fine-tuned to an incorrect direction, your single head-off layer can still project a majority of such representation into the final label. And if we replace the single head-off layer by the multiple head and also infer their identity with the TI function, and you can see they have a severe performance drop, a similar pattern as the TI errors. And this result tells us that for the continual learning with pre-trained model, the TAP is no longer equivalent to the WTP and TI, but should complement with each other. And we also have a formal explanation that for the regular continual learning problem with randomly initialized data training from scratch, because your randomly initialization and the subsequent task, they have no correlation. So you can regard them as a conditional independent, and then you can decompose them equivalent to the two sub-objectives. But for the pre-trained data, which incorporate a lot of pre-trained knowledge that are highly relevant to your downstream task, right? Then you can perform transfer learning to improve the performance, and then it's no longer conditionally independent between the pre-trained data and the downstream task. So it's not equivalent to these two anymore. And our solution is very straightforward. We just keep everything as a third objective that we optimize the remaining correspondence between the pre-trained knowledge and your downstream task. And in the practical use, it's just like to optimize the single head-off layer that projects all the instructive representation to the final prediction. This is essentially the final step, so it can rectify all the potential problems. And we further prove that these three sub-objectives, they are both sufficient and the necessary to optimize the continual learning performance with the pre-trained model, and also applicable to different representative continual learning scenarios. And further, we construct the method and which can explicitly optimize the three objectives. And the first, we construct the particular architecture of the task-specific tuning parameters, which is to learn the task-specific knowledge and to optimize the WTP within task. And also, we construct the task-shared tuning parameters, accumulate knowledge to accumulate especially the task-shared generalized knowledge. And also, we cover the corresponding representation to learn the task identity inference, the task classifier. And also, we recover the representation of the task-specific instructive representation to optimize the final task adaptive prediction function. And although our motivation of design this method is to optimize explicitly the three objectives, but finally we find it have a similar organization as the CLS series, right? You can see the left side, the hippocampus net, this have a task-specific encoding, and the right side is the neocortex net, they have a accumulate task share or generalized information, and these two models we replace their representation to enable them complement, and also within the hippocampus net it has a selective retrieval. And so finally we do the experiments with the different kind of pre-trained model and the downstream task. Compared with others, state-of-art methods that are essentially empirical design, and our method we explicitly optimize the objective. You can see we achieve very strong improvement in different scenarios. Right? We also do the ablation study to prove that the three components both they are all important to the or contribute to the performance lead. So that's all technical part. Let's do a very brief conclusion. So we argue that continual learning is a very good target of bridging the biological learning or biological intelligence and the machine learning or the artificial intelligence together, because both of them, they share the common goal of adaptation and survival in the real world. But their specific implementation maybe have some differences, which provide a space for their mutual inspirations. And for our extensive study of forgetting the forgetting problem, it's enjoyed a much broader concept, function, and a mechanism within the biological brain, and such has the potential to inspire continual learning. And from our study, we find the biological function and the mechanism, they should also follow the fundamentals of machine learning, because both of them, they try to learn a similar projection from the continual learning tasks input to the output. So they must share some underlying computational principles. And on the other hand, the exploration of such machine learning fundamentals can also help to understand the biological function, especially at the level of computation, which is also demanding for the neuroscience research. And I believe a lot of you, maybe you just come and to learn continual learning. And if so, welcome to read and follow the. We have a latest survey of continual learning, which cover almost all papers published in the recent years. And it takes me more than a month to read more than 500 continual learning papers again and to summarize their recent advance in the theory, method, application. And especially in our archive version, we have much longer and content we can include a lot of technical detail to make it user-friendly and to attract more people to join our continual learning community. So for my future work, I will continue to focus on the crossroads between the artificial and biological intelligence, try to establish the computational model, including like the brain-inspired AI and machine learning, especially continual learning, and the AI for science, especially for neuroscience, and we want them to support each other and fusion together. And if you are interested in this topic, I'm more than happy to chat in the workshop or afterward in the main conference. So, at the end of this talk, I want to use a beautiful picture to summarize all the content. This is a gift from a designer friend, and you can see there is a staircase moving forward and represent the goal of continual learning. And this shape is a carbohydrate, which is DAs, right? And at the end of it is a human-like robot that represents the fusion of the biological and artificial intelligence. And shed a light, and the light is 5 compartments with our software learning system, but it composes the shape of the human brain, represents the power of evolution, and also it has a lot of surrounding, a lot of 0 and 1 represent the power of computation. I think this figure will summarize what we are doing and what we will do in the future. Okay, thank you again for listening and welcome question.
We will have time for a couple of questions from the audience. Okay. So from me, I would have a question. You have this this slide where you were putting all of these types of forgetting. Do you have it here? Can you go to the slide with the different types of forgetting that you had at the very beginning?
Yeah, this one. This one, yeah.
So whenever we are talking about active forgetting, there is also a certain relation to machine learning.
Yeah.
What are your thoughts on how we would tackle machine learning, maybe from a more neuroscience-based idea? Is like, are the two concepts linked together, or there's some gaps that need to be covered for moving from the aspects of machine learning and forgetting? It's not as simple, right? Like from the neuroscience perspective, you can just not erase that knowledge in such easy way.
Yeah. Actually, I believe that learning have a very close correlation with continual learning. When the field began, we also surveyed a lot of paper on it. And because both of them tackle a very similar problem that forget something and remember something. But I think it's have more difference from the biological forgetting, because the objective is different. You cannot choose to forget something, right, from the human's mind, but in the machine we can manipulate, or we hope to manipulate them to remove something. And currently the machine learning have a lot of new work, and they have similar form such as like a facial information weighted parameters, that kind of things. So if we can do the underlying mechanism correlation with the current continual learning work, maybe we can go back to compare it with the neuroscience understanding. It will be a very interesting question.
Thank you. Is there any other question? And let's thank the speaker one more time. Is Chen here? Yes.
Do you want to present on your machine?
Please refer. The thing is that you want to join the Teams call? So maybe you can put for a moment the placeholder for her and we solve it in a second. So do no, not yet. Okay. So now we will have Chen Zhao, who did her PhD in Peking University, and now has been working in KAUST in the King Abdullah University, right?
Of Science and
Of
Technology.
Science and Technology. And she will give a talk on towards more realistic continual learning of the scale. So it's the floor is yours.
Thank you very much for the introduction. Hello, everyone. My name is Chen, and today I would be very happy to share some thoughts from our group. According to the recent work on continual learning from our group. So first, I would like to introduce the continual learning people in our group, which is called IVO. On the left is they are the PhD students and postdoc research scientists working on continual learning on the right, and they are our collaborators. And also we thank them for like the great works we've done together so far. Okay, so first, maybe let's have a brief overview about what continual learning is. I know many of you have known it, but yeah, let's consider why we need continual learning. So for the general learning, we just train, we have all the data at hand, and we train on the data once, and we deploy it in the real world, and that's it. But for continual learning, we continuously do it. And we learn it on some data, we deploy it, we predict, we do prediction. And when we have the new data coming, we train again on the new data. And we try to adapt to the new environment, right? So why do we actually need continual learning? And let me give you an example. So on Twitter, so we have different kind of messages, trees from time to time, right? So let's say like in 2019, the hottest topic is COVID. But when it switches to 2020, it becomes the Great Election. And then now it moves to vaccine and the World Cup. So the information or the data distribution is shifting over the time. If we just use the previous model, train on previous data, it is very hard to predict accurately on the new type of data. Okay, so that's why we need to continuously train or tune the model on the newly generated data to adapt to the new distribution. Okay, and how, okay, I'm gonna do it louder. How are we gonna do continual learning? Okay, I'm gonna talk this way, and if you cannot hear me, raise your hand. So why do we have a specific, why do we need this workshop to talk about continual learning? When we have the new data coming, can we just train on all the current data and previous data? Again, right, why don't we do this? First of all, this is a waste of our computational resources because we have already got a model on the previous data. If we train it again, so that will cost a lot. And second of all, we might not have access to the previous data. For example, the hospital data, right? When we train on with this hospital and we move the data to another hospital, they might not have access to the previous patient's data. And also another way to do continual learning is, why don't we just do the fine tuning, right? So we know the paradigm of using the pre-trained model and fine tune it on the new task or new data. Can we just do fine tuning? But that will give us a headache of catastrophic forgetting, which means, okay, we can fine tune on the new data and we perform well on the new task, but for the previous task, we might forget what we have learned. And when the data of the classes, for example, from the previous task come, we might not be able to predict. So people have proposed various methods to overcome the catastrophic forgetting. For example, they use the regularization-based methods, which means, okay, so to mitigate forgetting, we try to constrain the parameter change in the learned model. Okay, maybe some part of the parameter that is very important to remembering the past information, we constrain them, we regularize them, and we only allow part of the information to change. And people then realize, okay, why not just use a small portion of memory to store some previous data? So when we learn the new data, if we can train it on the new data, as well as the part of this old data, we might able to like remember also the past knowledge, right? So in this path, we have done a couple of works, and also we don't restrain ourselves to the image domain. we generalize it to the video domain. So the first work is benchmark. That gives us a standardization assessment for all the continual learning on the video domain. And the second is, given the budget on the memory, how can we smartly allocate the memory for the frames or for the videos? Okay, but these are not the works I want to talk about today. So what I want to introduce to everyone is some new thoughts on continual learning. So people have done this a lot around the memory, but is it actually necessary? So they use a small portion memory and they try to remember information from the past. But what if we don't use the memory at all? At the beginning, people didn't use it using the regularization-based method, but the performance was very poor. But can we do more? So in this work, we try, so at each new task, in this work, we don't have any memory. We don't store any data from the previous task. But for when the new task is coming, we use a synthesizer to synthesize the data belonging to the previous classes here. And when we actually train the model or tune the model, we use both the synthesized old data and the new data belonging to the new classes, and we jointly train the model. And that will give us a very good performance that can match even the performance using a memory. Okay, so another way to think about it, nowadays we all have the pre-trained large model, right? So they are very powerful. They are trained on huge number of data samples. So can we assume that they have known and they have learned everything, right? So if new data is coming, so can we directly use the model to predict for the new data? So according to our experiments, it's not that, so the large pre-trained model is useful, but if we don't do anything, we cannot reach the maximum performance. So given a large model here, pre-trained, we still need to use some learnable modules here. This is how we design our model. So this pre-trained model is fixed. That's why we can maintain the initially learned capability in it. And to adapt to the new task, we have a small number of parameters that learns on the new data. And of course, throughout the learning steps, we don't want to forget the information we learn for all the new tasks, right? So that's why we design an online module. And at each step, we accumulate the knowledge we learn from the online module to the offline. So that keeps the information of all the previous data information we have learned. Okay, and we designed a different variants using this parameter efficient fine-tuning. For example, use prompt tuning, adapter tuning, LoRa tuning, and all of them gives a very good performance. So this new framework gives us some thoughts. Okay, using the pre-trained model, let's just tune a little bit. Okay, and this is the work on the images, and we also use the prompt tuning for video understanding, continual video understanding. Okay, so this is the first question. And we focus a lot on memory. And the people in the past, okay, can we not use memory? Can we use memory? Can we restrict the memory? Can we just don't save? So many discussions about memory. But is it that important? Why do we focus too much on memory? What is the real important thing? Why? Let's see this. No, it could disappear. No, okay, maybe here. All right. Okay, so what is more important? Okay, so the reason we discussed a lot about memory, okay, two reasons. First, we need to store using memory, and that takes some money, right? We need a disk to store all the past examples. Second, we have the data privacy concern. So what if there are some laws that doesn't allow us to store the previous data, right? Let's see whether these two reasons hold. First, this table gives us the cost for the memory and also compute on different data sets. If you compare the cost for the storage and compute, we'll see that they are just very trivial amount. If we can afford these amounts to compute to compute for every fine-tuning stage in the continuing learning step, this is nothing, right? I don't think this budget is an issue. And also, is it data privacy issue? So we have a lot of works in the literature saying that given the model, we can most of the time we can reconstruct actually the data we trained the model on. And also in the work I just introduced, we can actually synthesize the images from the previous tasks, right? So in that case, even if you don't you don't have access to this data, you can invert the model to get it, you can reconstruct it. So what's the point? So we say that, okay, we don't care about memory. It's not a realistic setup. What is more important is the computation, right? It is expensive and it is slow. So in this new setup, in the continual learning framework, so we have every task, we have the data pair reviewed, and we update the memory using the new data. And whenever we try to fine tune our model on the new data, we give a computational budget. Computational budget, we can regulate using what flops, right? And the energy we use. And for simplicity in our setup, we use the number of iterations actually that each method takes, right? So given this, what will happen? Okay, on the left, it is when there's no restriction on the computation. So there are different, so these curves for different colors represent the methods in different categories. And there are distillation-based methods and sampling-based methods, or some methods that focus on the FC full collection layer. And you will see that, okay, the fancier methods work better. But if we constrain the compute for all the methods, so all the methods, we given the same number of iterations to allow them to compute for every step. We'll see the simplest URM. We just random sample without any design, without any extra computation. This performs the best. Okay. So this is when we have the hardware control. When we have the computational constraint. Okay. So if we have the computation constraint, can the simplest method train on at least one iteration on all the data? So for previous setup, yes, people assume that at least one iteration, we can finish that. But is it the truth? So now let's shift our attention to another setting of online continual learning. So previously we didn't care about whether it's online or how the data is generated, being paced. But in reality, for example, in Twitter, the data keeps coming, right? People keeps uploading uploading different images, information to the server. So we cannot stop it. And we have to continuously train the model. The truth is that, let's say that the speed of training the model is 35K tweets per minute. But in reality, the speed of data generation, data uploading is 10 times as large. So that means what? We just use the fastest way to train it. We cannot cover every data sample. So in that case, if we still use a previous setup to evaluate the method, it cannot reflect the real situation, right? The previous one means for every step, first, we evaluate on the new coming data. We predict on the newly generated, newly arrived data. And then we train on the new data when the label is ready. And for the next step, when the new data comes, we directly train the model on the second data. But this is not the case, because this has assumption that the data stream will wait for the model to complete. But definitely this is not true, right? So the more realistic setup is what? In every step, yeah, we train the model, but it will not finish until the second batch of data is coming. So the second data will be not used. We'll have a delay in using the data. And at the third, maybe batch, okay, when the model finishes training, we start to use the data. So in this case, some data will be not used. Okay, so in this case, we can tell that, okay, the faster model will have an advantage, right? So let's say that's a model, the method A, it is as fast as the stream. So it is able to train on every single data point. but for method B, which is 2 times slower than the stream, and it will skip some batches of data in the middle. Although it will still need to evaluate on this data. You will see that if we don't care about the capability of the model, we'll see that this method B definitely will not be as good as method A. Okay, this is the case. So using our new setup, considering the delay of the computation, we'll see that the more advanced, sorry, can I go back? Methods, unfortunately, they cannot perform as well. But for the simplest method, they perform the top on various setup. Okay. So this is when our computation, when we have the computation budget, we cannot catch up with the generation of data. But even that, so if we can cover the data that's already uploaded, are we able to have the labels of all the data? Right? So still this this figure. Okay, so we generate in the speed and we train and in the speed. And what about human annotation? Of course, that depends on how many human labels are used, right? But usually it is not possible to annotate all the data generated because it's very expensive and also it's time consuming. So what happens is that we only able to annotate part of the data. So we have the mixture of labeled data and unlabeled data. So given the budget, still the computational budget, we have the labeled data, a small portion of all the pictures we have, and the rest of them are unlabeled. So we need to wisely allocate our budget to process both of them. So in this figure, this blue one is showing that if we only use the labeled data as before, so as we grow, as we increase our computational budget, we'll see that performance does increase, right? Because we can train more epochs, more iterations on the labeled data. It will give us a better performance. But at a certain point, it will overfit the data, right? Because and it runs enough sufficient epochs, and the performance will go down. It overfits the labeled data. A better case is that if we do use unlabeled data at the same time, it doesn't overfit because when we increase our budget, our computational budget, we can utilize more and more unlabeled data. But a naive case cannot give us a very good performance even if it doesn't overfit. So in our work, we try first we wisely allocate the budget among 3 parts. So the first, the current labeled data, in the labeled data in the current task, and the unlabeled data in the current task. Also, we have some data, labeled data from the buffer, right? 3 parts. We need to design, you design a mechanism to allocate the resources. And also we need to use not only the labeled data, and also we need to use unlabeled data using self-supervised learning, right? On that route, we design some mechanism like autoencoder reconstruction. We have the loss to represent the self-supervised learning. So the 3 loss terms will bring the curves from here to here, from here to here. Okay, so this is when we have only part of the data annotated. What will happen if we have 0 annotation? Is it possible? Okay. Of course, we want to do this because annotation is a headache, it's expensive. No? So it's the pipeline of annotation is what? We have the arbitrary source of data, a lot of data, and we need to clean it, to curate it automatically, and then we use some human effort to iterate it. That's a complex pipeline, and that needs a lot of money and human effort. So let's think of
Evan? Evan, are you ready
Yes,
for
can you
presenting?
hear me?
Yes, we can hear you. And
Okay, and
wait 1 second, I will put you on full screen. Okay.
okay, you can see my screen?
Yes, and we can hear you. So whenever you're ready, please start.
Thank you. So hello everyone, my name is Eden Belwada, and I'm here to present our paper entitled Multi-Ode or Rehearsal-Free Multi-Head Incremental Object Detector that I co-authored with my colleagues Arnaud Daponi and Kevin Bailly at Dataka Lab, Paris. So rehearsal-free class incremental object detection allows agents to learn continuously from streams of data, where the goal is to continuously learn new objects, new class objects as they appear with the time. And the sets of data in the states can overlap. However, only annotations of the new class boxes are present at time t, and no annotation from the past is allowed. At inference, of course, we expect that the model can detect not only new class objects, but also those of the past classes. However, the absence of the annotations for past class objects leads to two main problems. The first one is catastrophic forgetting that you all know, which means that the model, when it tries to fit the new data distribution, it completely forgets the past one. And the second problem that is very related to the first, we call it background interference, which means that the old class objects in the new state are not anymore annotated, which leads to their consideration as background. And this aggravates the effects of catastrophic forgetting. So we propose Multi-Ode, which is a rehearsal-free class incremental object detector based on CenterNet. The latter is a fully convolutional object detector, and the reason why we selected it, it's because it's fast, very lightweight, and easily compressible and deployable at the edge. So CenterNet encodes objects by their central point by using one center map by class, and then regresses their size and offset using one shared offset and size maps. So we modify CenterNet in order to adapt it to a continual scenario and also to improve its efficiency. So we notably exchange replace the ResNet 50 backbone with the EfficientNet B3. We changed the upsampling network that consists in upconvolution networks and deformable convolutions by a feature pyramid. And finally, instead of having one shared size and offset maps, we use one size and offset map by class. And the reason for that is to separate the class representations in order to prepare for the continual learning. So in the first stage, we train the model with all the data of the first classes available. And once these are trained and we want to learn the new classes, we freeze the backbone, we freeze the feature pyramid and the class maps, and we add a new feature pyramid for the new batch of classes and their class maps. And here we apply transfer learning between the classes that were learned in the first state and the classes learned incrementally. During inference, we apply class-wise non-max suppression to remove the redundant boxes within the same class. So we vary the size of the backbone, and we evaluate on two versions of Pascal VOC dataset, and we also use amnesia detection for ablations. We vary the number of classes in the states, and we use two metrics for the evaluation. The first one is the mean average precision with IUU threshold of 0.5, and the second is the harmonic mean between the mean average precision of past and new classes. We compare the method against some distillation-based continual object detectors, and we find that despite the fact that our method performs worse in terms of training from scratch with all the data, it outperforms all the other methods in most of the tested configuration with subsequent margin in terms of both evaluation metrics. And contrarily to the authors of CenterNet, we have found that the use of non-max suppression during inference helps with removing the false positives of the classes without influencing those of other classes. So to conclude, Multi-Ode is rehearsal-free class incremental object detector based on transfer learning, and it does not require saving previous model as the methods based on distillation. However, it can have problem of scalability if the number of classes increases too much within the time. For the project for which Multi-Ode was proposed, we had just a few classes that appear in video stream. So we did not have that problem for our specific use case. And also the second limitation is the fixed representation. So the quality of the model depends on the quality of this fixed representation. So if it's trained on very few data or very few classes, the transfer can not work as we wanted. So this is it, and thank you. Don't hesitate if you have whatever question. So can you still hear me?
Yeah, then I was muted, sorry. I do have a question for you. I mean, now in the last slide, if you go back to it, you were talking about the limitations, right, of scalability.
Yes.
The thing is that you have some other work yourself and with your colleagues, right, with you explore the feature projection. So in the case, in some of the use cases in which you will want to have multiple object detection, could you try to learn some kind of intermediate attribute or characteristic, that you can project so that you can overcome the scalability problem when you add too many classes? Or do you think it's something that requires more nuanced solutions?
I actually, the thing with this project that I actually was a bit limited with the time. I mean, we had some ideas about exploring how to handle this task, but since we were focusing on, actually the use case was a bit different. As I said, we had in our case, we had very few classes, I would say maximum 7, that occurred during very long video streams. So that's the main reason why, since we did not have this problem in our use case, I did not really have the time to explore the intermediate features, but I really think that it can be interesting. And also, instead of having during inference all the class maps that activate at the same time, we can have some gating mechanism that help us decide before which of the heads can be better for this batch of classes. And we can also, instead of adding, for example, for each batch class, adding just like that the heads and the feature pyramids, we can also use intermediate features and similarities to decide maybe if the new classes are not that far from the old ones, we can just simply use some shared heads instead of just creating, maybe we can have just some redundant heads that we can just avoid with this method. But I did not have time to work on that.
Okay, so future work, I guess, no?
Yes, yes, I hope so.
Okay. There's another question. Do you want to just come here and talk here? I think it will be the easiest.
Can you hear me?
Yes.
Okay. So I have a question here. In this setting, when you add an additional, for a new group of classes, you add an additional module on top or head for classifying them, right? Yes.
Yes.
So now in the end, how do you predict from which head do you get the classes? Like you have a new image or something and you're classifying or predicting on top of that. So which head do you use?
I actually, in the current state of the paper, all the heads are activated at the same time. But what helps in I will say cleaning the prediction is the class-wise non-max suppression. So the class-wise non-max suppression works class by class, and for each class is gonna remove the false positives. And we have found that with this simple method, this non-max suppression helps a lot in eliminating whatever redundant boxes that we can have. But I mean, I agree with you that in a better situation, we can just say, as I said, maybe we can use some gating mechanism or or some function that can, based on similarities, just tell us which is the best head to use.
So can you explain quickly what you do, like with this cleaning or this, in the end, how do you decide right now what you are using?
You mean how the non-max suppression works?
Yeah, you said you were doing something to decide, like some simple solution, some post-processing.
Yeah. So the non-max suppression, how it works is like we take for one class, we take the B box that has the most confidence from the model. And later we will check all the B boxes that overlap with it with a threshold that we call the IUU. And if this threshold exceeds a limit, it means that the two bounding boxes, they highly overlap. We just delete the B boxes that highly overlap and they have less confidence. And in this way, we keep the bounding box that has the highest confidence without having repetitions in the bounding boxes.
Oh, okay. Got it. Thank you so much.
You're welcome.
Thanks a lot, Eden. Maybe we thank the speaker one last time.
Thank you very much.
And we will now go on to our lunch break, right? So we will be back. Do you want to put the loop or?
Just the presentation. We go to this building to there.
Yep.
At 3:45.
Yeah, there was one session. This is the PPTX.
Yep. So share with me. When should I go and install that?
I think maybe
by laptop and software, see the type. Right. You can use this one. Do we have a adapter for HDMI? I think that's fine, yes? Yes, maybe it's fine.
We would like to share all the slides of some people at the streaming. We're asking for them, but we will have to talk with the speakers later. So we will put it in the website of the workshop for all those that we have available.
Yeah, the ones
No problem.
so they limited some media explaining their solutions. If you want, we can either hook you up, like just move your presentation to one of our laptops and you can present here.
Great. Okay. Okay, we are back with the next speaker, Amal Clanentricky. She's a senior research scientist in DeepMind, and she will be talking about rethinking evaluation for continual learning, a case for efficiency. I'm looking forward to it. Please.
Thank you very much. Hello, everyone. Thank you, Mark, for the invitation. It's really great to be here with you today. And thank you all for coming back after lunch, actually, despite maybe the jet lag hitting now. So today I'm going to tell you about an exploration that kept us busy for the past few years, actually. This exploration was triggered by the observation that scale and large transformers and models actually change dynamics and practices. With these large models, now we are more and more in learning paradigm that is divided into pre-training phases and fine-tuning phases. But we've also seen that scale changed the behaviors of models when it comes, for example, to forgetting or to transfer. We therefore started thinking about the place of continual learning in all that, and how can we actually make it more useful for practitioners today within this changing landscape. So talking about practitioners, we started by the observation that, paradigm shift or not, continual learning is actually already happening in machine learning. If we think about the typical life cycle of a machine learning practitioner, when we are faced with a new problem with its new data, we first actually start by looking at what has been done before, either from our own experience or from others. We can then borrow ideas, reuse code, and hyperparameters leveraging this prior knowledge. And then we can build on it to add a few more things and a few more things, and eventually getting feedback from other practitioners and injecting it into the system. So we can see here continual learning happening on a task level from the practitioner point of view or perspective. It can also happen at many other levels. For example, as a practitioner sees more and more tasks, they can learn to set what is needed for it more and more quickly and efficiently. We can call it experience, knowledge, or intuition, but the result is that over time we can get to results faster and better. Continual learning also happens across practitioners. Through sharing code or papers or blogs, etc., we can build on each other's experiences. But all of this is actually happening extremely inefficiently, consuming a lot of time and resources in a non-automatic way, relying heavily on humans in the loop and on processes that can take sometimes months, like publishing, for example. So the question we asked ourselves is how and what do we need to inject some of these continual learning mechanisms already at play into automatic learning systems? So let us go back to the model perspective and the model world. Nowadays, with foundation models taking the center stage of machine learning, the model's life cycles are divided, as I said, into expensive training phases, followed by more or less expensive deployment phases. While there is some build-up of knowledge between training phases through human experience, most of it is still largely inefficient and not automated. Moreover, the models are not updated through deployment, potentially discarding sources of data that can provide useful information to the model. So can we accrue the knowledge differently so we can learn the next thing in training or in deployment more efficiently? The North Star that we work towards is a system that leverages information from every source of data it encounters to grow its own knowledge. This can be translated into an overall more efficient system that can allow us to grow the model further in terms of scale and data within the same budget that we have available. So with this goal in mind, we started in an exploration focusing on adaptation and consolidation. What I will present today is divided into two axes. The first part is a benchmark that rethinks the evaluation of continual learning and adjacent topics with a focus on efficiency. And the second is the study of online learning with transformers. So the first access or the first step of the journey actually brought us to land on NEBIS, the never-ending visual classification stream. When we started thinking about how we can make the models learn continually and more efficiently, the first question we asked ourselves is, are the benchmarks that we have available now and the metrics that we are using suitable for that? Do we have benchmarks that are large-scale enough, that isolate the question of knowledge accumulation enough, and that puts efficiency at the center of the question? So with this question, we set sail with this amazing group of people. It's a large group. And rather than creating yet another benchmark and building on the idea that continual learning is already happening in machine learning anyway, we considered the changing interests of the computer vision community as a source of tasks. So we looked at proceedings of different venues and from conferences, journals, etc., that we sort chronologically over time. So we can consider that as a community in computer vision, we did this continual learning process over the years. So on that, we laid out a process to acquire tasks by randomly sampling a fixed number of papers per year. And from each publication, we extract data sets that are used within these papers. We then remove data sets that cannot be cast into a categorical problem, or that are deprecated or have legal issues that make them not suitable for an open and public benchmark. But we also remove duplications within a window of 10 years to avoid having ImageNet every year. So after that, following this process for 30 years of computer vision research, we obtained a sequence that consists of more than 100 tasks with a total of 8 million images. In this stream of 100 tasks, we can see a few duplicates. Around 10 datasets actually appear twice in the sequence. And you can see that the tasks are naturally diverse and their distribution is not stationary in an interesting way. We can see, for example, different domains such as texture classification, satellite imagery, or medical image analysis with COVID, for example, appear and disappear over time. We also observe that the average size of datasets grow over the years. So for the first version of the benchmark that we open source, we stopped at 2021. But by following the same procedure, we can actually extend the benchmark in an unbiased way to include proceedings that are published in 2022, 2023, and so on. The resulting stream is not too small, but not too large scale either. It can help us iterate research ideas on it. And each task in isolation is relatively very well understood. We actually targeted classification in particular to avoid other confounding factors to play with knowledge accumulation, so that the stream is actually focused on this question of knowledge accumulation. So now the question is, how can we develop and evaluate and compare learners on this stream in a robust way? The choice that we made is to actually compare learners on a Pareto front of compute versus error. The computational cost here is measured in terms of flops on the whole stream, which also includes the cost of hyperparameter setting on a task level. The error is averaged, however, on a part of the stream that we held out as meta test. I will say a few more words on that later, but it's never, more importantly, that it's never used during the development phase. So it's actually future tasks that the continual learning system doesn't see until the evaluation time. In particular, we held out the 3 last years, or around 30 tasks for meta test. This can help us, as I said, assess the ability to efficiently adapt to future tasks and to avoid that we overfit actually to the test splits in the stream. Further, we actually allow multiple passes through MetaTrain to do some, stream level cross-validation and hyperparameter setting. But once this is done, we do a final run on the whole stream, where during which we actually, compute the computational cost in terms of flops, as I said. We also provide 4 splits per task. That means train validation, a test split for development that we use for hyperparameter setting on the stream level, but another test set that the evaluation doesn't see until the final run. So again, to avoid overfitting to this test set in the training stream. Then, with the intuition that memory is actually not that expensive, but compute is, we allow actually revisiting past tasks. We also allow revisiting past models, but such access can penalize the learner in terms of compute. And finally, to allow for testing different ideas with limited resources, we also provide a subset of tasks that we randomly select that constitutes a short stream of around 24 tasks that can be used for prototyping. So with this in mind, this new evaluation protocol, let us see how some baselines behave when learning from this system. In this series of experiments that I will show later, the goal that we wanted to show is to assess actually the usefulness of the benchmark. So what we wanted to show is that the problem is hard enough, but that's also, neither too easy nor too hard. So the existing simple baselines allow to solve some questions, but there is a clear space for improvement. So we have, independent baseline, meaning learning independently on each task. We have fine-tuning baseline with actually dynamic selection of the previous task. For that, we use a simple similarity measure based on zero-shot performance using frozen feature extractor from previous tasks followed by a KNN. And we compare that to actually how random features behave to decide whether to, select the previous task or reinitiate the model. The pre-training baseline is actually built on top of the vision encoder of the Flamingo model. And the multitask baseline selects either all the previous tasks or the most similar tasks, similarly to what we did with the fine-tuning approach. And finally, for the Bayesian hyperparameter selection, we just replace the random search per task for hyperparameter with the Bayesian approach. As you can imagine, the only benchmark or approaches here that actually can leverage some knowledge accrual are the fine-tuning approach and the multitask approach. So the first discovery that we made, actually to our surprise to a certain extent, is that fine-tuning surpasses multitask. So the baseline that we show here is actually the best multitask baseline that we found. And so we were actually, when we set up for this exploration, we were expecting the multitask to actually be better in terms of performance, but more expensive. What you observed is that even if we add all tasks, the amount of negative interference makes that the fine-tuning approach, the dynamic, simple, heuristic for fine-tuning approach actually works better. We also observed that the pre-training gave a significant improvement over the independent baseline, but in terms of performance, the improvement is not significant compared to the fine-tuning and the multitask approach. Just a quick comment here, the pre-training baseline actually includes the cost of the pre-training, as you see here. So if you remove this cost, this is brought a little bit earlier in the flops axis. The second discovery is that dynamic fine-tuning of this simple heuristic for selecting previous tasks actually continues to improve even on top of a pre-trained model, even if this pre-trained model is of a good quality, like as the one used in Flamingo. So to better understand how methods actually fare on each task, we, in addition to this Pareto front, we did another analysis looking at the relative improvement compared to the independent baseline. So let us look at these curves within a slice of fixed budget. In this figure, this is actually relative improvement compared to the independent baseline, as I said. So a horizontal line shows similar performance to independent, while a negative slope shows that, we have improvement compared to independent baseline on these tasks. So a first interesting observation is that, all these curves are actually flat towards the end, around the 9 last tasks. These tasks actually are all from the X-ray domain. They are all COVID data sets. So this shows actually a clear limitation of the current approaches that are not yet capable to transfer well to these, relatively minor domains or not well represented in the rest of the stream. And they are actually also not yet capable to accrue knowledge efficiently over time because all these tasks are closely related. So even that we see them in sequence, we don't improve, within these 9 tasks. We also observe that all of them show linear improvement over independent. While this is expected for most methods, we actually expected the fine-tuning or a smarter way of fine-tuning to become more performant as it sees more data. Basically, we would like to achieve a curve that becomes faster over time. Overall, this confirms the interest of the benchmark. So we clearly see that transfer has an impact on the behavior, but there is also a clear room for improvement here. Actually, just a quick remark that this is a proposal of metrics, but given that we have repeated tasks in the stream, we can also reuse the classical continual learning metrics if we are interested. One that we looked at in the paper is forward transfer, where we compare actually if we can do better on the second time some of these tasks appear compared to the first one. But yeah, I mean, if you are interested in forgetting as well, the benchmark allows for that. So in order to understand better this transfer mechanism, especially for the fine-tuning dynamic, the dynamic approach, we looked at the structure the algorithm automatically discovers from the data. And we found that many interesting observation through that. First of all, we see that this simple heuristic discovers a rich and non-trivial structure in the data. We also observed that, not surprisingly, ImageNet is a hub, but many other hubs appeared. We observed that some of these actually are clustered nicely and intrinsically by domain. You can see OCR, natural scenes, or texture, for example. And that the algorithm is able to discover a long and complex path for knowledge transfer. So overall, the graph shows that even with simple heuristics, we can already leverage interesting substructures in the stream, confirming that studying better transfer is a rich and promising direction for future research on this benchmark. So let me conclude on this first part. First of all, we've seen that the stream is interesting and challenging, and it comes with a relatively novel evaluation protocol. The series of baseline actually showed that transfer leads to better results. We also observed that hyperparameter search is robust, but largely inefficient. So there are multiple ways of improvement. Even if you have some ideas on which direction to look at, there is a long way to go. And in order to solve this knowledge accrual problem and ultimately improve efficiency, we can find inspiration in many other domains, not only continual learning, but meta-learning, AutoML, to learn how to deal with non-stationarity, to adapt faster when new data come, or to automate this hyperparameter search. So our hope is that the benchmark can be a common ground to many research fields that study this question of transfer knowledge accrual from different angles, and that we join forces actually to get closer to our dream for a more efficient sequential learning. The code of the benchmark, along with the evaluation protocol, the baselines, are open sourced, and we would be very happy to guide anyone who would like to attempt that. And of course, as a benchmark, this work led to more questions than answers. This is a non-exhaustive list of questions. We started exploring some of them. In particular, one that I want to highlight is the modularity axis. And on the back of the work with Nevis, a subset of the team actually released 2 interesting works, Diloco and Tipaco, that I invite you to take a look at. I personally, with another subset of the group of the team, actually looked at a different direction, which is the question of continual adaptation of pre-trained transformers downstream, and the interaction that can happen between in-context learning and online learning. So this is actually a good place for me to take a minute to ask you if you have any burning questions about this first part before we dive into the second. Yeah.
I mean, from all of these 100+ data sets that you were checking, like maybe a couple of other details, like how much of them are fine-grained data sets? Because I think the ImageNet being a hub is also very related to all of these fine-grained data sets or sequential learning of very specialized data sets, and all of them benefit already from any ImageNet or brain model that has this kind of like more context on objects. Can you give a bit more data on this?
Yeah, so actually in the paper, you will find the list of all the data sets that are included in the stream. I don't remember, we don't have maybe necessarily statistics about, you know, fine-grained versus coarse classification. But I mean, for example, CABS isn't there, CARS isn't there. There are actually data sets that are really fine-grained. They don't necessarily appear after ImageNet. Some of them appear before. So it's, you know, all depends on what the community used at a certain point of time. So, I mean, the fine-grained data sets are part of what the community used in many works. So naturally, they appear in the selection. But the main, you know, idea is that we didn't want to impose any prior idea on what data sets to select, and we really relate that to the community, you know, by randomly selecting papers and publications. Yeah.
I was wondering if you could clarify in your evaluation that you mentioned, was the task identity available in Bernstein or not? Because I think in the past years, we've seen that it makes a very significant difference in how difficult continue.
That's a great question. I mean, the results that we have here are all task aware, so we don't have any task agnostic results, but this is a very interesting direction to explore further. I mean, you know, obviously one complication is that here we have different classes, different number of classes per task, so not being task aware adds another complication, but it's a great direction for research for sure. Okay, let us move forward. We still have part of the presentation, and if you have other questions, I hopefully will have time for it later. So yeah, let us now dive right into this, revisiting online learning in the era of transformers. So before, let me start with a quick motivational or remotivation. Again, on the long run, we are interested in systems that continue to learn even at deployment. Now, focusing more specifically on transformers, when we actually set up for this exploration, one of the challenges that we were facing is that transformers are trained with a fixed context window, but that can be then exposed to data at deployment that can far exceed their context size. Online learning came straightforwardly as a way to adapt to this incoming distribution and to go beyond the fixed context of the model through essentially turning the weights into states that can, you know, either complete whatever is in context or interact with it in interesting ways. So now the question we had is, how does this memory in weight actually interact with the memory in activations that comes from in-context learning? And can it actually offer interesting opportunities on top of that, especially now that we are seeing longer and longer context sizes? So let me say a few words about, you know, turning weights into state first. We can imagine various approaches to actually implement gradient-based adaptation in a sequence that goes beyond the context. We tried some of them, and we found that, you know, simple transformer Excel style with key and value caching to be the most promising. This method actually allows us that when new tokens arrive sequentially, we can take gradient steps only on a relatively small number of tokens, for example, 256, while actually attending to tokens that are coming from previous gradient steps within a rolling window, let's say, for example, 2048, that is the total length of the context. Doing online learning, you know, or online gradient descent in this way, while at the same time scoring the sequence, essentially turns the model parameters into states as the weights slowly adapt to the incoming data. We analyze this online learning approach in two scenarios. First, I'll branch out a little bit from vision to go into language, where we actually evaluated the log loss of long sequences with a transformer-based language model, where the sequence far exceeds the attention window. looking at books, for example, they can consist of hundreds of thousands or even millions of tokens sometimes. And in this scenario, we can consider each book coming, with its own distribution that can be more or less similar to the generalized distribution that the model has been trained on. The second scenario we looked at is the challenging problem of online continual learning in vision. We focus here on prediction models, and we consider a slightly different objective. There is the cumulative next step log loss that comes from the frequential minimum description length literature. So let us start from language. Here is actually a closer look at what typical results look like in this scenario. We take a generally pre-trained model trained on a broad mixture of texts, and we use it to score a sequence of books coming from the test set of the Project Gutenberg, concatenated in a single sequence of text. The pre-trained model is further fine-tuned on a varying number of books to control the amount of distribution shift before we start this online phase. We sequentially then score these tokens and record the cumulative next token log loss throughout the whole sequence. And here we can see three alternative models. We can see the static model that's represented by the blue line, to which we actually compare a dynamic model that continue to update throughout the whole sequence, and a dynamic model with resets in which we actually switch back to the pre-trained generalist at book boundaries. The plot here shows the cumulative log loss relative to static evaluation, and similarly to the curves we've seen before, a downward slope means that we are accumulating less loss, while an upward slope indicates that we are accumulating more loss. We can also see the book boundaries as the green lines here, and we see clearly that adaptation generally improves predictive performance, especially when we are faced with a long sequence. You can see one in the middle where actually the slope goes more and more downwards. In the next slides, we'll show actually interesting trade-offs between the computational cost and performance depending on the distribution shift. So for this set of results, we vary the model context size and the frequency at which we take gradient steps online to vary the computational budget. We observe that when the models are faced with a significant distribution shift, that's the one on the right, we see that the models with smaller context exhibit better compute to performance trade-offs than the models that are with larger context. When we are, more and more on distribution through fine-tuning on the PG19 training set, this advantage is slowly reduced and even inverted. Online adaptation, however, unsurprisingly, always improves the performance of the models in this set of experiments. And moreover, the shorter context model and with online adaptation can achieve a competitive performance to the model with longer context, but without adaptation. This can be more expensive in terms of flops, obviously, but it comes at a lower memory requirements. The second discovery we made comes from the way that we choose to operate online learning, this KB caching mechanism. As a baseline and alternative to that, we also investigated a simple overlapping or rolling window approach. With this approach, previously observed tokens are re-encoded at each gradient step. For example, if you have an overlap size of half of the window, that means that each token is actually encoded twice in the sequence. So this is obviously computationally more expensive, but this higher cost doesn't necessarily translate into a better predictive performance. Instead, we observe that the transformer Excel style with KV caching is typically slightly better, not only in terms of cost, but also in terms of performance. So yeah, the takeaways of these studies are gathered in this paper. You can scan the QR code if you're interested. And the main takeaways are the following. First, we basically confirmed that was known before, is that dynamic evaluation almost always lead to better performance. The new thing, however, is that this dynamic evaluation typically has a positive performance to compute trade-off, especially when faced with dealing with large distribution shift. So now building on these new learnings, we go back to vision, and reusing the same KV caching mechanism, we added here two components to be able to deal with the problem at hand. First, we need to use transformers in a supervised setting, ideally while still conditioning on previous labels. To do that, we propose two ways of operating this conditioning, either through feeding image and label consecutively to the model as separate tokens, or by adding a projection of the labels to the keys and values, and in the same time making sure that we mask out the prediction, the current prediction, so we are not conditioning on the future. We also, as I said, as we are looking at the online continual learning problem, we added a replay mechanism. So we make use here of notion of replay streams that is introduced in this paper here. With replay streams, we actually at the start of learning, we start several streams of data where one of them always goes forward in time and the others are randomly reset at the start at each step. The first setup we looked at is a toy experiment with extended MNIST. We study here a sequence of 100 stationary tasks. Each of them is composed of 1,000 samples that are coming from 10 out of the 47 classes that are present in the dataset. We also randomly reassign labels to these images. And we go in an online fashion throughout the sequence. The online learner is agnostic to task boundaries here. Boundaries are simply sudden events when the distributions of the observed data and the labels actually changes. And from the perspective of the learner, even previously seen inputs will very likely be associated with different labels now. Which actually it keeps changing. So it's the model never sees the exactly same point of data twice. What you observed is that after initially struggling during, let's say, first 20 tasks, the model learns to become a highly efficient few-shot learner that only requires a few examples at the beginning of each task to make accurate predictions. This indicates that there is some kind of spontaneous meta-learning that is happening through this interaction between in-context learning and online learning. After that, we move to a more complicated setup, which is the CLOC benchmark. I know if you are familiar with this benchmark, it's a benchmark of continual geolocalization. It's a long sequence of 37 million images coming from different locations that is chronologically sorted. To give you an idea about how challenging the benchmark is, actually prior work struggled to get to 45% of performance, even with pre-trained or strong pre-trained feature extractors. And even less than that when they are trained from scratch. To our surprise, this simple combination of online learning and in-context learning that we propose here actually led us to reduce this error on this challenging setup by more than half. But also, you can see here this approach here is, learning from scratch. With that, also combining online learning and in-context learning actually helped a lot. Yeah, what is between brackets here is the feature extractor, and all of these are followed by 4 blocks of standard transformer. So our takeaways from this line of work are gathered in this paper again, if you are curious to learn more. And the main takeaways are that combining in-context learning and online learning enabled interesting meta-learning behaviors, sustaining progress over long sequences of data, but also this combination led to strong performance on hard real-world problems. Okay, I think we are almost at time, but this brings us to the end of our exploration anyway. The message that I would like to leave you with are the following. So the work on Nevis first showed that there is an opportunity to achieve more efficient sequential training. Beyond the playground that it offers, it is a call for us to join forces across, related but currently independent research streams. It is also a protocol for generating benchmarks that could be generated to other problems or domains if we are interested. The work on online learning showed that online learning at inference can be both more efficient and more performant, especially when we are faced with a significant distribution shift. It also showed opportunities in combining in-context learning and online learning beyond the question of efficiency. A caveat to these results is that obviously online learning can pose important safety problems that needs to be addressed when we go forward in this direction. But finally, my main message here, what I want to leave you with, is actually a call or an invitation to put future performance and efficiency at the forefront of continual learning. While forgetting is an important problem that led to many interesting insights, I personally think that the past is only useful if it helps us to solve present and future tasks. It can also increased efficiency can be a means for us to push the boundaries of our models. More efficient models can make them actually more accessible to more people, but also it can help us scale them more within similar budgets, without speaking about the environmental impact of all that. So this is what I want to leave you with. With that, I would like to thank my collaborators for the amazing work and thank you all for your attention. And I hope we have a couple of minutes for a few more questions. Yeah, thank you very much.
So for questions, I would like whoever wants to ask a question to come forward to the microphone so that we can let the people online or hear the question. Another way I can start with one question. So you were talking now, especially in the last inclusion, you were touching again about the distributional shift. And for me, I would like a bit of clarification that whenever we talk about distributional shift, usually you talk about on the input. Yeah. But since there's also some directions for continual learning that go towards domain shift, which is more like toward the output or how we represent classes, concepts, zero locations, which I was not aware. Do you think that there's any conclusion that you can also extract from this that says, okay, the distributional shift will also work in domain incremental when concepts are shifting, or the conclusions are very clear at the moment on the input?
Okay, I would like to think a little bit about this question. So actually, we didn't really focus on a particular type of distribution shift in these results. So if we think about the language space, for example, the models are pre-trained on the C4. I think I'm not sure how many long sequences it contains, but we do see a clear shift between that and the books data set actually. So that's, I mean, I don't know how much this relates to these types of distribution shift in vision. Going back to vision, the pre-trained feature structures we played with most of them are pre-trained on ImageNet, and we then move into CLOC. So that's a clear distribution shift, not only in terms of input, but also in terms of domain. So I think it doesn't really matter the type of distribution shift as long as the representation that we have is maybe less valid for the data that we have at the adaptation phase. Then we are interested in continual adaptation to achieve both better performance, but also potentially in some cases more efficiency.
Thank you.
Great speech. You mentioned last that the past is only useful if it is helping us with current tasks and the future tasks. Can you talk more about it? Like what scenario is this in this sense?
Okay, that's a personal take, okay? My opinion is that the field developed around catastrophic forgetting for understandable reasons. It led to many interesting insights, but maybe focusing too much on forgetting led us to somewhat suboptimal local solution to the problem. Also can lead to a loss of plasticity because we are focusing really more on stability more than adaptation. So what I would like to achieve personally, and also if we think about how humans think and operate, we don't necessarily remember everything like the way that we try to make our models remember. we remember things that are useful for us. If things are not reused in our experience, they are naturally forgotten. This can leave space for more learning as well. They are also not remembered in an exact manner, but more in an abstract, conceptualized manner. So with this in mind, I think if we actually focus our metrics more into the future, maybe with efficiency at the center, as I said, we can make our models build on this experience in a more efficient way and naturally discard the information that is not useful to go forward in our experience and become more and more efficient. Yeah, thank you.
My question is about backward transfer. Mostly online continual learning rates are very below zero backward transfer. I was wondering if you also measure this metric. How did it work? How was it measured in work?
Okay, thank you very much. Again, with this, future-looking idea, actually important experiences, I would say, would represent themselves into our future. If we think about Nevis, for example, the datasets that have been used mostly by the community are actually repeated in the stream. The way we selected them makes that it's repeated only once, so we don't have multiple steps. But with that in mind, the question of backward transfer can become also forward transfer if we see again, the task again in the future. We did study that. We actually, in the paper, we have multiple fine-tuning strategies. I show only one here that was the most performance, but we have also, fine-tuning only from the previous task. We have privilege information fine-tuning where we have, the transfer matrix of all the tasks as input, and we fine-tune from similar tasks. And what we observed is that this privilege information transfer can lead to really better performance on the positive transfer on the dataset that are repeated the second time they appear in the task in the stream. So yeah, again, I think if we focus really on what is useful going into the future, we can see that, experiences that are really important will be repeated, and then we can, all these metrics can be refocused into a forward-looking scope.
Okay, thank you. Let's thank our speakers one more time.
Thank you very much.
Self to you. So now. No,
okay. So I was saying, I mean, for the purpose of this talk and the works that I'm gonna present, we are interested in class incremental learning. So we have that, each task corresponds to a set of categories, and then at the test time, we have no task ID information. So I don't want you to sleep on slide number 1, so I will go straight to the point. And the point that I want to make in this talk is that really, if you want to build models, you really need to build strong foundation. I don't know what's going on because that's still another message. But anyway, on Zoom.
Sorry.
Yeah. Okay, perfect. Okay, we need strong foundation, but then we do have strong foundation because over the years we've been building stronger and stronger model. And, of course, we started from CNN. I'm doing computer vision. So, and then we went to visual transformers. And nowadays we have large multimodal models. But then we have to be able to use these models. And this may be not that trivial, especially if we are in a continual learning setting. So, of course, if we have a large pre-trained model, maybe they can have they can be an important source of information. And so we will ideally be able to use these large models also in this continual learning setting, and in particular in class incremental learning set, as I will show you today. But then we have challenges, and the challenges are many, but I decided to focus on 2 challenges that we have tried to address together with some of my PhD students. And the challenge number 1 is that we do have knowledge in these models, but this knowledge may be hidden. So we need to be able to somehow discover this. And in particular, we were interested in leveraging this pre-trained model for performing continual learning in an unsupervised way. And the second challenge is something that we have done more recently, and it's about, of course, we have larger model, but then this, of course, create issues in terms of computational cost and scalability. And so how do we deal with that? So I will start with challenge number 1. So this knowledge that is in large pre-trained model may be hidden. And if you have no supervision over the different tasks, how do you get this knowledge out? I will start with something a bit old, because we have been presenting this first work some years ago in ECCV in Tel Aviv, but where we started to study a problem that is called the class incremental novel class discovery. So, the motivation is actually something quite reasonable. So we have been dealing with the data for which we don't have supervision since many years in computer vision. So encountering samples of unseen classes, it's clearly inevitable. Then we have a different range of addressing this problem. So we may have methods for open set recognition. We may have methods for unsupervised clustering, but here we are interested into something that has been invented by other colleagues and is called novel class discovery. And the problem is that we want to exploit a set of images where we have labeled information, and we know that we have a certain number of seen classes. But then we want to discover in a labeled data set a set of unseen classes that are related to the seen classes, but they are not exactly the same. So this is a bit the formalization of novel class discovery from a visual point of view. So we have labeled data of a certain amount of known classes, and then we have unlabeled data of other classes that are somehow similar but not related. So we have somehow that the set of classes in the old and in the new set are disjoint. And the problem is this one. You want to recognize the novel classes on the unlabeled set, and you want to leverage knowledge from the labeled set to do that. This is, of course, not continual learning yet. We started to look at this problem, and we saw that the way this problem was originally formulated by a researcher from Oxford was that there were some very strong assumptions. So the first strong assumption is that you have access to the labeled data. The second assumption is that the novel classes are available all at once. And then the second thing is that we are just interested, the third thing, sorry, is that we are just interested in the performance on the novel classes. But these three assumptions are too strong. So indeed, I would like to still have knowledge from the labeled data, but maybe I have only access to the pre-trained model, not to the labeled data. I also don't, I think that it's more reasonable the fact that you don't have synchronous access to the labeled set and the unlabeled set, but this may change over time. So it's a bit more reasonable that the samples of the novel class arrives in session, like in continual learning. And then, of course, we would like to maintain good performance on old categories and on new categories. So, of course, we don't want to forget it. And so this is a bit the visual formulation of the problem that we called class incremental novel class discovery. So at training phase, only the model associated to the old classes is available. And then you have access, of course, to the data of the unlabeled set. And then you are interested in having good performance both for the old classes and the new classes, because you also want to discover these new categories. To do that, we designed a method that was the first. It's reasonably simple, but also reasonably effective. So this method, we call it FROST, feature replay and distillation with self-training. And even the name itself contains all the elements, the technical elements that we put in our architecture. So we have a first phase where we are training the network on the labeled data set, and we are also storing some prototypes that will be useful later on for feature replay. And then the architecture is very simple, and we have two categories of losses. So first set of losses are the one in blue that you see on the bottom of the picture, and are the one that allows somehow the task agnostic discovery. So we are inheriting ranking statistics loss from a previous work on novel class discovery. We have a consistency loss because, of course, we have no supervision, so we need some form of consistency on augmented data. And then our novelty, but I didn't want to report the formulas. It's a loss that allows self-training on the data from the new classes. And this allows also to perform something that is important if we are moving toward continual learning, the fact that we are building a classifier that can be task agnostic. And then, of course, we are, as I told you, we are also interested in retaining good performance on the old class. So for forgetting prevention, we also put in place some knowledge distillation at feature level, and also some generative feature replays given the old class prototypes. This is really at very high level what we proposed, and this is our first result. So here, basically, there were only 4 methods on novel class discovery. We moved them into our scenario, and our method was somehow the stronger. Importantly, was the only one who was providing very good performance, both on the old and the new categories. Of course, this, as I told you, was just a first step, because then we decided to move this research a bit ahead. And this is a paper that is currently under submission, where we wanted to exploit this idea a bit more in depth. And we wanted also to exploit a bigger pre-trained model for the same problem. So the motivation for this second work is actually the plot that you see here. So basically, if you are taking already a large-scale pre-trained model, the performance are already better than the one that you can get if you are training your model on the labeled set. And also another important observation is that even if you are then taking a pre-trained model and then fine-tuning this pre-trained model on the labeled set, you don't gain too much. So why don't we just use this large-scale pre-trained model, and we try to develop a method for novel class discovery based on that. So this is a bit the visual transition. So this is novel class discovery. You do have joint access to labeled data and unlabeled data, and you want to discover the classes in the unlabeled set. This is class incremental novel class discovery, that one that we have just discussed, where basically you don't have joint access to labeled data and unlabeled data, and you are doing some self-supervised learning on the unlabeled set. And this is what moves us towards continual learning, because it's a multi-step class incremental novel class discovery, where we have a first phase where we have a pre-trained huge model, and then we have several steps. And in these several steps, we are progressively discovering categories over different different steps. We didn't even call the methods that we tried methods. We call them baseline, because the main takeaway of this work is actually that if you design something relatively simple, is already very, very strong. And so the thing that we propose is that we first take a visual transformer as a backbone, then we use a cosine normalized linear classifier as a classifier, and then we train this network with clustering laws like sync-or-non-op from self-supervised learning literature. And then we also saw some pair class prototypes that are used in the learning steps. And this is a bit of the illustration on the methods that we're basically using this self-supervised loss derived from sync-or-non-op for the current data, while we are using some feature replay with some variation in order to replay the feature for the classes that has been discovered over time. Overall, this is a kind of simple recipe, but then this can be used to somehow have prototypes for all the classes that we have discovered over time. And so we are able to do some form of task agnostic inference. This is a bit some of the results that we got on relatively simple data sets, but the main takeaway is that the two methods that we called baseline, and in particular baseline plus, are already very strong compared to the previous method. In particular, the best competitor is Frost. That was the method that I presented to you before. Of course, performance varies according to different settings, but overall the message is clear. This baseline plus is pretty much strong. Something a bit more interesting is this one. And the thing is, we took two existing methods from other colleagues that are AutoNovel and Okra that were used for novel class discovery. And we simply plug into these methods, pre-trained models and some cosine normalized classifier as we were doing. And in all these methods, this led to a consistent improvement according to forgetting and accuracy. Okay, now I'm going a bit outside of this and I'm showing you something pretty much more recent. So at a certain point, we said, okay, now we have a bunch of works for novel class discovery, but then we are simply discovering categories, but can we give them names? And this is something that instead we have presented this year at iClear. There is no continual learning in this work, forgive me for that, but I thought it was still interesting because it's a natural evolution of the previous work. So this is called democratizing fine-grained visual recognition with large language model. And the idea is that we have a small collection of images for which we don't have annotation. And then we want to learn a classifier that is able to operate at very fine grain. So we are inspired by the way humans work, right? So we see images of some concept. We don't know nothing. But then we do have tools now that allows us to discover things and also to recognize them at very fine grain. So we have an interplay of three players: vision question answering model, large language model, and a vision language model. And then we are starting to do some form of reasoning like the one that you see here, that of course we automatically implement, but you also want more, because out of this reasoning, we also want to be able to build a multimodal classifier that allows to tell us that this new image corresponds to a strange animal that is called cardinal. So the method that we design, it's quite complex, but it's overall made of 3 steps. So a first step is to translate visual information into textual information. So we took our small set of images without any annotation, and then we use a visual question answering model to identify the super category name. Then we use an LLM to output a series of attributes that can describe well these, the different birds in this case. And then given the images, given the super category names, and given the attribute set, we do another query to the visual question answering module, and then we also output an attribute description set. So overall, this allows to have several elements that are used in a reasoning pipeline to discover a set of feasible categories, but very fine-grained. This is unfortunately not enough because these category names will be very noisy. So we have some refinement thanks to a multimodal model that allows us to filter out the unplausible fine-grained categories. And this is more or less what brings us here, where we have identified all our fine-grained categories. But as I told you, this is also not enough, because at the end, we also want to build a multimodal classifier that can be used for future images. And this is what we are doing in the step number 3. I don't provide much detail, but I wanted to show you, and so this is the inference step, but I wanted to show you a bit what is happening in the first part of the pipeline. So you have your unlabeled images, then you identify the super category, then you acquire the expert knowledge, and you see here, given the class doc, you're getting all these attributes, but then attributes are not enough. So you do another refinement thanks to this list of attributes and thanks to the images, and you get this more sophisticated description. And given all these, now the model can reason and can tell you that maybe this image corresponds to this special type of dog. Of course, this is a bit the high-level idea. Then, of course, we need to compare with the state of the art. The problem, as you may imagine, is kind of new, because this is not even fine-grained classification, because we don't use any supervision. We use external knowledge. So we compare with a bunch of methods that are unsupervised methods. That you see the method on the top. But actually, the best, the most performing baseline was a new RIPS paper that was presented the year before, that was using a retrieval pipeline to discover a known concept. But even compared to this paper that is quite strong, this case, our method, it's much, much better. And in particular, this case, it's a bit better perhaps to recognize a large variety of concepts. But when we go to fine-grained, definitely our approach, it's the most performing. And these are some examples of what we are able to discover. So, of course, we have a situation where our model is doing really good. We have a situation where our model is doing better than the annotation. And unfortunately, we have also a situation where our model output partially correct prediction, but still, we can be kind of satisfied. So somehow the mistakes that are made are not that bad. Then another natural question that can arise is, what about if I take, some strong feature structure, and then I plug some, classifier on the top, and I fine tune these models, where our methods stand. And actually, it's quite strong, quite remarkable that Finer also outperforms some learning-based methods that use some strong baseline like CLIP and Dino. Okay, the last part of this presentation, it's about the other challenge that I mentioned. So somehow this large pre-trained model need also, when used in continual learning setting, need also to, be used in a way that it's computationally not too much heavy. And for this, I choose one work that we are presenting next month in Collas. So this is about another topic that is multi-level class incremental learning. And we have designed a method that somehow summarizes patch tokens in a smart way in order to reduce the computational complexity of the approach. So we choose a class multi-level class incremental learning because it's a bit more challenging setting than the classical class incremental learning, especially when we have to deal with forgetting, because basically what we are seeing as foreground classes at a certain time may be also classes that we have seen before, but then they are not annotated at step T. So somehow this makes the catastrophic forgetting a bigger problem. We have also another issue in multi-level class incremental learning, the fact that we have a long tail distribution of the classes, and this makes everything more complicated. That also has implication on the kind of methods that people have been used for multi-level class incremental learning that were not prompt tuning methods, even if these methods are actually when we started to work on these the strongest on the market. So we decided to address this problem with the architecture that you see somehow here. So you have your pre-trained strong model, but then we want to train a set of parameters for each incremental step. But then, and then we want to use all the trained parameters to make the prediction. However, if you naively implement this is gonna explode. So you need to be a bit smarter. And so you need to limit the computational requirement. And to do that, what we propose is that we want to summarize somehow the internal representation of the visual transformer. And we want to summarize this like we see in the picture here, where we are introducing some trainable tokens that we call patch selectors that allow somehow to summarize the patch token in a smaller dimension that is then used for prompt tuning. So this is a bit at high level a picture that show how our architecture work. There is a first, frozen forward on a classical visual transformer architecture. And then there is our contribution. Let me show you entirely. This is practically what is happening because we are summarizing the patch tokens with this block that is implemented in this way, where we are basically learning some importance for the different representation. And then we are using this summarized token in the multi-head attention. And then we are finally dropping this and replacing this. So, and something important that I didn't say, this can be trained with a single binary cross entropy loss. So this is also quite convenient because we don't have to add all the losses that we could typically add in continual learning. And these are briefly the results. So when we develop our method, the best competitor for multi-level class incremental learning was this method, KRT, that we have evaluated for different buffer size. And you see that, somehow our approach, even if it doesn't use any buffer, is quite strong. We have also compared with Coda prompt, and we also have some results, but I didn't report it here, where we are using our method also for the classical class incremental learning setting. Is not the best method, but it's still quite competitive. Very last slide about this. Of course, we started to say that we devised this strategy of selecting patches in order to reduce the computational requirement. So we also evaluated this. And somehow, even with one selector, we get quite, these are the figures for one selector and for 20 selectors. So we understood that somehow enough information can even be encoded in a single summarized patch. And then another experiment that we have done is to compare our strategy with another strategy that it's not using continual learning, but it's a strategy for token merging, and our approach is somehow also competitive. Okay, I'm concluding now. So, of course, I presented everything before, this era of multimodal foundation models beside the ICLR work. But then, this makes me think what will happen for this idea of discovering novel categories in the future. I do believe that this idea of continual learning of novel concept is still cool, but then we also need the proper benchmark to evaluate this. And at the moment, this was clearly a limiting factor, at least in our work. We've been working on novel concept, but these novel concepts are just novel classes. This is not much interesting anymore. I want to go either to fine-grained classes, or I want to go to novel things, meaning like novel action, novel object, human-object interaction, novel concept in rare domain. So I do believe that there are areas where this idea of discovering novel concept could be a bit more interesting, and now we are perhaps ready to move there. And then a thing that we didn't investigate much, but we plan to investigate a bit more. This is also related to the previous talk. Of course, computational issues are of utmost importance now. So when we are building on large model and larger model will come, we really need the strategy to do this well, especially in continual learning. So with this, I would like to thank you, and also thanks my collaborators. Actually, both Ming Xuan and Thomas, they're the first author of all this work are here, so most of their work is really their energy. All, I would say. Thank you. Of course, I mean, many of the co-authors are here at CVPR, so they will be glad to chat with all of you.
Great. Okay, are there any questions from the audience?
Thank you for the great talk. It's a quick question. The last work on the prompt tuning for the multi-lane, I guess. Considering you didn't have a buffer explicitly, what aspect of it do you think was avoiding the forgetting?
What's that?
What aspect of the model was helping overcome the forgetting?
I mean, technically, this method is a parameter isolation method. So we've been having over the years several type of design of this. So of course, then if you're deciding to address this specific problem and you go for a parameter isolation, but then you don't put the constraints in the number of parameters, this is clearly unfeasible. But overall, that's why for me, I mean, that's the way to see it. Okay.
Maybe since you talked also about this work that didn't have continual learning, but it's still, I think it's still hopefully more people found it relevant, but would you like to say a few words on like what would be the connection with continual learning? Or I mean, if you have some plans, maybe you're waiting for another publication.
No. I think I can comment on this. So somehow, I mean, one thing, you know, that at least for what we have done in my research group is that at a certain point, we also have some work on self-supervised continual learning over the years. So at a certain point, we said, so how far we can go if we don't have any supervision, but we still have a stream of data organized in tasks and something like this. So this at this point, it's not reasonable anymore, right? Because I mean, given all the evolution of the things that are happening in the community. So what I do believe is that we have to, of course, maybe transition out the supervised setting that it's not interesting anymore, but maybe we grab some auxiliary supervision from external models. That is somehow what we are doing in the reasoning things. I don't think that at the moment these models possess all the possible knowledge. I would believe that you still need to, design continual learning models. Eventually, you need to change the way we formalize the problem, the way. So I do believe that, large language model, captioning models are other sources of information that can be used in a weakly supervised approach, but still in a continual and incremental learning setting. So they are not totally disjoint, in my, of course, personal opinion.
Thanks for your answer. Anyone else? Okay, then we will take a moment's break to set up the panel discussion, and in a few minutes we will start with it. We will have some questions that we will start with, then we will be accepting questions from the audience, at least if you get any inspiration on things that you would like to ask. Yeah, that's very good.
learning and non-stationarity in the general sense became my focus since 2020, and I continue to work on that now. Very nice to be here. Thank you again for the
Thank you.
invitation.
Welcome. Sorry, I was also troubleshooting.
Today, all the workshop is like this. Don't worry. Let's take it to like. So I'm Elisa Ricci. I'm a professor at the University of Trento in Italy. Actually, I'm the less experienced here because I've done some work in continual learning, but I wouldn't say it's my primary research area. I have done a bit more work on domain adaptation on different, different settings. And then, of course, continual learning can be related, right? Because we do have distribution shift, but then we also want to learn over time. That's why I got interested into this. And also the second point, I had a couple of students that fell in love with continual learning. So they put me the challenge, to start looking at this field. And in particular, I really was interested for a while to this learning continuously, but with very weak supervision. This is a bit what we have done.
Thank you. Welcome. Okay, so then maybe we can start with some questions that I had prepared to get the conversation going. As you know, like we can spend a bit of time for each question. I think if the debate goes on, just take it over and please talk with each other or discuss the ideas. But if not, like let's keep some room so that we can do more questions. And then later we will ask the audience if there's some other questions that they are interested in. So for starters, I think something that a lot of you have brought on are pre-trained models and large language models in general. There's from the foundation models, lately we've seen these RAGs, the retrieval augmented foundation models, and they can access new data in a knowledge base at inference time. So maybe a bit related to what you were just talking about. And the question will be like, if you see these as a form of continual learning in the aspect that you want to consider, and if you think that it still makes sense to continually learn the model weights in this age of RAGs or like large language model, maybe later large visual models. Whoever wants to take it first.
For me, would be similar to what I was trying to express before. I mean, like one of the baseline I mentioned in the work of the ICLR work is actually a baseline based on this idea of retrieving related concepts. So it's really related to this. Of course, this was not continual learning, but as I was saying before, I mean, I don't see this as an alternative. I see this as a stimulus to build stronger continual learners. But this is the way I see it at the moment.
Mm-hmm.
Yeah, from my idea, I don't think RAG or that kind of thing is itself is a continuous learning model, but I think it's maybe a very important part of an idea of continuous learning model. Because it's just like a similar rule as a replay buffer, right? It's just like not a replay, but it's just like such a data buffer that you can provide some beneficial information. And in fact, the study of RAG or do some fine-tuning of the large language model or pre-trained model, which one is better is still not under explored. And the current idea maybe the both of them work together can get a better performance, like a complementary effect. And from my view, it's just like the key question is the content of a parameter or data, which one is better for compress and represent knowledge, and maybe they have a complementary form, just like the human brain, and to do it.
Yeah.
Responses?
Maybe not really response, but building up on these two excellent answers so far. Also going back to maybe the part of the presentation where we talked about online learning, to a certain extent is actually a combination of this retrieval or data based adaptation and weight-based adaptation. So let me actually answer with a couple of questions. If you consider RAG alone, would it be possible through these mechanisms to become more efficient or more performant the second time we see data? I don't think that's the case. So maybe weight learning can complement that from that perspective. but also to which extent would retrieval augmented systems be able to adapt to OOD data? I think that's also another challenge where weight adaptation can help with. But it's I also see them as complementary, not necessarily working against each other. And I think there are interesting effects that we can achieve by studying more of this combination in a more systematic way.
Yeah, this we are lacking a little bit now. I mean, this is a systematic way of going.
Yeah, I think part of this answer probably I gave during the morning too. And when I personally feel there are two ways of looking at it. One is, I think where foundation models are being used. I still think, at this point in time, I think we're in a transitory phase where we're going from LLMs being a fun tool to it getting used into mainstream applications. I think we're still going through that transitory phase at this point in time. And I think when we go through the transition and LLMs become important for search or like large contemporary applications, I do think information needs to be more current. It cannot be data that's trained up to 6 months ago, 1 year ago, things like that. So which means I do think a notion of continually learning becomes important. Whether RAG will achieve that or not is something that we still don't know at this point in time. I think that's one way of seeing it. Another thing is also that I think there are many applications. I think often the foundation models are directly applicable in web scale problems, which is the kind of problems we all deal with on a daily basis. But I think there are many other applications, medical, probably in a remote oil refinery or under the ocean or things like that, where still narrow models continue to work, shallow models continue to work. And I think those settings continue to be good cases for continual learning because they're not connected to the web in a general sense. So I think there are many applications which, due to security reasons or just geographical reasons, may not be connected to the web. Then continual learning continues to make sense in those kinds of scenarios.
Interesting. Okay, maybe we move on to another question. So we also, so we have that the loss of plasticity in continual learning may prevent models from learning new information, right? Like, I mean, we have to be aware that we do want this stability, right? Because we want to get the information that we've already learned, but we also want to have the plasticity to be able to add things. If we focus on mitigating forgetting only, this can exacerbate the problem when the models become so stable, right? Because you don't have that much more capacity, for example. Do you think there is enough empirical evidence supporting the presence of the loss of plasticity when we are reaching these points of stability? Or do you see this as a real problem that happens in real world applications or closer? Or do you think is more of a made up scenario from some continual learning scenarios?
Sure. So, I mean, I do think, going back to, I think some of the comments that were stated by the others too, I do think we need to envision newer benchmarks in continual learning. I do think that's something that's important, and this perhaps related to this question, because I think a lot of the benchmarks today are 5 tasks, 10 tasks, 20 tasks. So that's largely where most of the work is. There are a few works in 50 tasks, 100 tasks, but then a lot of them are just in this 10 to 20 task regime. And I think that's probably not enough to study this problem well enough. I think we still don't know when the capacity of model gets saturated. When do you need to? I think one question that I personally feel has not been answered well enough in continual learning is, when do you train from scratch again? Right? So when do you say, okay, we need to do it periodically? Obviously, I think it's quite evident that you cannot keep learning continually all the time. There has to be some points in time that you reboot and start from scratch. So how often do you do it? When do you do it is still an open problem in continual learning at this point in time. So I think that maybe better benchmarks for doing this, having more long-term continual learning with larger number of episodes and so on, I feel may give us more clarity on this. This is my initial thought.
Yeah, Anthony, for the current benchmark, I think I still kind of feel very clear the loss of plasticity And maybe a lot of people that work on computer learning experiments may have observed phenomenon that you all tunes have a parameter, right? All the long term that stabilize old knowledge. If you had a stronger or larger parameter on it, then the older memories will be returned better, and the learning of each new type will be interfered. It is very obvious phenomenon, and because the network capacity is limited, and this is a diamond of the new and the old. And actually, these two concepts can be written at my talk in this morning by the generalization ability. That is just like to improve the space of the solution that can tolerate the distribution differences. But such generalization is also have the limited capacity, like because, for example, if you given model all the minima that is flat enough is only have a very small amount of them have the limited have the flat surrounding, but the flat also has some limitation. So anyway, the conflict is more like it depends on the whole capacity of the network, also the solution. Yeah.
Actually, going back to the question of if loss of plasticity is something that naturally occurs or not. I do agree that the current benchmarks are maybe limited from that perspective, especially regarding the length of the benchmark. So it's one of the motivations why we propose Nevis, not only for length, but also the variability of the data that we see that can help with that. Actually, if we change a little bit from supervised learning, if you go to reinforcement learning, then loss of plasticity is much more clear and obvious. And it comes from, maybe this interaction between the agent and the data itself. So the mechanisms are different, but these are very real problems where loss of plasticity is obvious. Continual learning research also looks at these problems, and I think there are multiple interesting insights that we can, share across these domains as well.
I guess similar to how in a reinforcement learning, a lot of the time there's also like this resetting that he was mentioning about, right? Like, oh, let's at some point it's just like let's reset the buffer, or let's reset the part of the model and so on. That's what you're interested in.
Yeah, I don't have much more to add. I remember what was said. I mean, for many things, I really think that, we are starting continual learning because we don't have the data to do a systematic analysis of the phenomenon that have been occurring. So unless, and this I also mentioned at the end of the talk, so if we don't unlock this part, it would be very hard to study things well. And also I like a lot the conclusion of your talk that you said, maybe some concepts we need to maintain, some concepts we don't need to maintain. So this is also something that we don't know how to do it now. So this is also part of that.
Okay. Well, I mean, then I will shamelessly plug a bit like the competition that was held a bit well, not a bit, it was held in the workshop. So as we will present later, and maybe some insight will be interesting, this year's competition from this workshop integrated continual learning with repetition and the use of unlabeled data, which are two concepts that I think are relatively novel. Or I'm not sure, like some of you that have been a bit longer maybe know of works with repetition or unlabeled data that are interesting and maybe are less known. An interesting result from the scenarios that we evaluated was that in some cases there is class the class repetition and the unlabeled data frequency increases. So when you will have less labeled data and more unlabeled data, which also it's kind of like what you probably want as a good scenario, performance improves. The fact that you don't have labels anymore, but you have an increase on unlabeled data seems to show that in some of the solutions that were presented, the performance was improving. Also, when adding distractors, unlabeled data that was nothing that we wanted to at that point classify in any way. Do you think that we can do continual learning with limited amounts of annotated data? So this goes in contraposition of what we were saying before, right? Like I know that we are saying, okay, let's use these things, but can we also do for other cases, medical data maybe? continual learning with limited annotated data and making use of the novelty detection on the learning from unlabeled data in order to guide a bit this learning, and how important is supervised learning in the early stages of any learning model, like any.
Starts, yeah. I'm actually wondering if, you know, some of these results are related mostly to a stronger representation. So building on your talk, for example, I mean, using unlabeled data more and more frequently can go in this direction, making representation that are less reliant on the spurious correlations that exist between the data and the labels that we have. So maybe this is one of the reasons why you see this. We also observed that during many of our experiments, like using stronger pre-trained model actually gives better results. So this is maybe an explanation to why using more and more unlabeled data leads to better results.
Maybe the question is, do we need to insist so much in unlabeled data? Because this is
This was the question. Right?
This is something that is a bit frustrating to me, because now I mean, it's true that, for instance, for some domain like medical data, getting annotated data, but still, you know, we can still retrieve related information. We can still use another model. So now we really have much more available tools. So I don't know if still, you know, just focusing on unlabeled data is the recipe anymore now in 2024, because we have so much extra knowledge. And even, you know, for rare domains, still this is, you know, will change fast. At this point, we are, you know, we have foundational model for everything, right? Yeah. In 2-3 years. So I don't know. Let's see.
Yeah. So yeah, the use of unlabeled data is always how direction that people want to explore and incorporate, and the use of more effective use and use more tend to get better. And actually, including me, and we in 3 years ago, we proposed a semi-supervised continual learning setting in CLVISION, and also have a lot of relevant work. I think it is as well.
Yeah.
And Kartik's work.
Kartik, it's over there, right? So it's like...
Yeah. And when I read this question, I think it's a wonderful question, because before that, people consider this problem is just like we consider some related context to design such a pattern label data setting like semi-supervised continual learning or such a thing. But there's a lot think about the given a setting when to in the timing of introducing labeled data or annotation can affect the performance theory. And actually, if you use this idea to think about this question, then this can cover a lot of relevant settings that at the early stage to introduce label data, it's very similar to the semi-supervised learning, right? The first strong teacher and the supervised one and so on. And the middle term is more like many current application of pre-trained model in industry. I know like pre-train for some time and then fine-tuning for some time, and then collect more data and then pre-train, continue pre-train, and then do continue fine-tuning and very rarely go up and down as like this. And for the at the end stage, later stage to do the introduce annotation is more like a regular transfer learning or right to do the doctrine. I think this to evaluate the timing, the influence on given setting, and also correlate this to other scenarios will be a very wonderful question. And I want to explore it tomorrow.
I mean, also, I guess what you're saying is that when you're at the later, maybe you want more sparse kind of annotation, and maybe it's a human in the loop kind of setting. Of like, is this a bit the direction maybe that you would consider like interesting, like to when you reach these later stages where maybe we're going to very specialized kind of knowledge or very niche, if having a human in the loop also with all of these pre-trained models, like it doesn't matter which modality you're doing, you can just transfer it to text kind of, and hopefully like does that align with something that we could be seeing later on?
I think so. I think that's definitely something interesting to consider. At least in our own work, we've thought about doing active learning.
Yeah.
Which is what it would be. I mean, you have to choose samples in later iterations, but we haven't got to it or tried that in a in our methods yet. But I do think, I mean, so we've done some work. So one of the papers I presented this morning was on continual personalization, where you only have few samples, which is the opposite side, which is you don't have as many samples. But one thing we did not study there is whether unlabeled samples will still further improve the accuracy. So I do think at some point, maybe the annotated data can be few, depending on what applications and what's the context of what's available. But I would expect that unlabeled data would be useful in whatever form, as long as your loss functions and other strategies are in place. That your representation learning strategies are in place. I think more unlabeled data should only help.
And it's cheaper. Any follow-up? Maybe we can open some questions from the audience. Whoever wants to ask maybe should come to the forward here and ask the question so that the people in the Zoom call can also. Anybody, or is there any in the Zoom call? Yeah, please. Here, take the stage.
Thank you. Thank you so much for the fantastic talks and for this panel. So the notion of attributes came up both in Elisa and Vinith's talk. Using attributes to describe images is an old idea. We have used that for zero-shot learning and so many different things. So two questions. First, discovering new attributes as a continual learning versus just combining existing attributes, right? The differentiation between these is something that I'm interested in, and like I think combining known attributes is an easier problem than discovering new attributes. So that's one. And two, the importance of these attributes being human understandable, because both of you were using language as a human understandable notion of attributes. So do we have to have human understandable attributes? Thank you.
So maybe I'll answer the second question first. So I do think attributes should be human understandable, especially if you want to look at interpretability, if that is a consideration. If interpretability or explainability is not a consideration, I think it perhaps doesn't matter. But I believe the fundamental premise of explanations or interpretations is human understandability. I think you need to have some shared intermediate semantics, which the model and the user agree upon. And that for us is language. And so for all of us humans, that shared semantics is language. So from that perspective, I do think the attributes, if you want that interpretability, have to be human understandable. The discovery part is something that's interesting. We have not tried that yet. I think what we have initially is just to bring the notion of concepts / attributes into the continual learning framework. I do think that's an interesting angle to study, to see if you could discover new things too. In our case, it was a little simple because we queried an LLM to get the attributes. We didn't have to really do much to do it. It was fairly simple. But I think discovery could be interesting. Could be interesting for something.
Maybe I'll also comment a bit. So this was a bit hidden in the conclusion of my talk, but no, it's but it was somehow there. So what I mean is, like, when at this point, I do believe it's not interesting anymore not to start appending just categories, right? But then an attribute for me is also a description, like an adjective that goes together with a name, right? And then now we can really go wild in growing the space of object and the space of attributes. And we also invoke compositionality. We can do a lot of things. These are things where I now started to work on, but not on the continual learning setting, but for other setting. But I also think now that it's also interesting from the continual learning setting. So I think now we have really the tool to scale this bidimensional space of nouns, attributes, and grow wild, right?
Yeah. Well, thank you very much for the fantastic questions. Actually, brings in a lot of thoughts. I want to comment a bit on the human understandability part. I see where you're coming from interpretability. I think actually beyond that, what I'm personally more interested in is to quantify how much we can trust the model. having human understandable attributes is one way, but maybe not the only way. The counter argument to that is that imposing a human view on the model can end up being less efficient. So actually, I think we need to think about all this hand in hand. But maybe the main question here is, what do we want to achieve with human interpretability? If it's model safety or usefulness, maybe there are other metrics that can be more suitable to the way the models learn, like, you know, quantifying uncertainty or something else. Yeah.
So just to add to that, I completely agree with that. Yeah, I think there's just one view to doing this, and maybe just a couple of zoom out thoughts, maybe 20,000 feet kind of thoughts. So I do feel that maybe we've got machine learning, deep learning itself in general to a point where you need to begin model development with user requirement specifications, which is something we do very well with software development, but we don't do that as well with machine learning model development, where you begin that with the user requirement specifications document where the user says what they want. Because even when I talk about interpretability or whatever it may be, to each user, it may seem they may want something different from what they want as output from the model. So that maybe I still believe the notion of shared semantics is something very important, that both the model and the user need to know what semantics is required out of the model, right? So that's something that you have to predefine before you start training the model. So I think in some sense that will set the tone for what you really need, whether you need attributes, whether you don't need attributes, whether they need to be human interpretable. I think it depends on what the context is set for that.
For the first question, I think it's very relevant to a concept of combinatorial generalization, right? And if we can achieve such combinatorial generalization, especially in a continual manner, I think it's a very cutting-edge problem that pursuing by many groups currently, and a lot of the latest work. I think it's just a start before, and also currently I don't have a clear answer, and we will still working on it. And also a relevant question is like if such a combination is better work at the parameter level or the data level, is also we are pursuing. And but for the second one, I think because if you concentrate on the explainability of the language, especially the language relevant information, this can increasingly may sacrifice some performance. But on the other hand, what I value for the large language model-based applications is that before that, if the language content is not that large amount, then the word or the text is just like a discrete point. But now, if you use everything into compress everything into a large language model, then it can just like support a continuous space, especially representation space, and then you can do some more like represent everything in it. And so I believe that if the language model is big enough, then maybe we can find a good way that increases the performance as well as the explainability of it.
Thanks a lot again for the question. I think it fostered quite a nice discussion. Anybody else has some question that they would like to ask? Please. Hi. It's not active, it's the laptop microphone. It will catch you. Oh, sorry.
Yeah. My question is, so there were talks about like scalability and stability and plasticity and, you know, larger tasks and stuff. But even like after years and years of papers, we're still even on the most basic settings of continual learning, there seems to be a disconnect between when you're doing like traditional learning, where even like on the simplest data sets, we just do, you know, we have access to all the data, as opposed to when you do it continually and really intuitively no information is seem to be removed. Like we still have all the data, it's just how we present it. And somehow we seem to, even with more compute, do worse than when the data is presented in like in the more traditional manner. So there seems to be we're fundamentally missing some piece of the puzzle in our learning methods. I wanted to know what your opinion is and where this sort of problem seems to lie on a theoretical basis, because like, we don't know, otherwise we would have solved it. Or what your like conjecture is on what we're missing. Thank you.
Anybody?
That's really a challenging question.
Yeah, yeah.
I have a few thoughts. So I think maybe a part of it is because of the metrics that we've been using. Maybe we need to rethink that a little bit to achieve what you described. Another thought that came to mind is that, maybe the reason why the multitask scenario is still outperform continual learning is that when we have all the data at once, we can see in the same time all the possible directions of the gradients and, achieve the compromise between them in a better way. In continual learning, the fact that it comes sequentially, we first go in one direction and then maybe we cannot correct it anymore in a good way. So actually thinking more about these gradients, how they interact, and maybe use that in such a way to inform how we should see the data, not only in continual learning, but also in IID, can both be beneficial to what you said, but also potentially improve the IID learning. So I really do believe in the active learning direction in better data selection. I think we've seen more and more evidence that the quality of data is, really primary access to lead even to better foundation models. So one direction that can, maybe lead to a better compromise between this multitask and IID learning is to look more at how to select data automatically through training, either in IID or continual learning.
Yeah, from my view, especially from a theoretical part, and actually in this morning my talk also includes some of such content that from a theoretical part we explain why some replay data may be very critical for in computer learning scenario, right? Because it is a very important part also to learn the full probability. And but this is assumption is mainly based on the training from scratch or for such a relatively simple problem that if you with appreciate or strong appreciate model, this can be largely avoided because of the further have already incorporated such the knowledge of this data or similar data. And actually for the practical use of computer learning, training from scratch or relatively simple setting, it has strong performance with a very strong limitation of the current application of computer learning method. But for the pre-trained model, basically do some very well designed method, then they can largely overcome this question. I think it will open an avenue for we make a computer learning method really in application.
I think that the question came that there are three settings we're talking about here. One is plain simple supervised learning where you train with a full data set. The other is continual learning. And the third is perhaps curriculum learning. Right. So I do think there are three things here at this point. And when we do continual learning, often a gold standard benchmark or baseline we compare against is what if you gave the model all of the data at one shot, right? So it is, so I would probably expect that any day to do better than continual learning. We do consider that to be a good and upper bound baseline for continual learning in many cases. But yes, I think perhaps the question gets trickier when you bring curriculum learning into the mix, whether it's useful if you train it in particular stages, hold back some data and bring in some data at a later point in time and train it. That is still, I don't have a very conclusive response. I do think that sometimes it works, sometimes it doesn't work just as well. So I'm not very sure about that too. But I do think there are three settings here to consider. If you only consider continual learning, I do think training with a full data set is probably expected to do better. So that's what I would say.
I don't have much to add, but I also think that this, the active learning dimension, I mean, it was already said many times, but then it also introduced some complication because I've started to work on a couple of things, because we really don't have solid methods to select, to deal with this uncertainty, right? This opens a bunch of other questions. And so, yeah, also there, we're still lacking a lot of knowledge.
Yeah, very interesting question. Maybe I can piggyback a little bit because I had already a question like written with curriculum learning and it's related, and maybe it fosters some more comment, and if not, we can move on. But some of the older work in curriculum learning, I'm talking more like 2015, so on, was already showing that that third scenario that you were mentioning actually allows to achieve better performance if you can have this quick look at what are the concepts that you would like to learn and then order them in the correct way. You could improve the learning by presenting the data in a specific order compared to just having the pool of all of the data, which will be the supervised case. I find it interesting because my question was also going in this direction, which was like, oh, those works seem to not continue to the best of my knowledge, like so much afterwards, but they're still quite interesting. And one of the reasons for me of why sometimes they are a bit forgotten is because even before pre-trained learning, but with large models, seems like if the knowledge base is very specific, like language or like certain object-based classification tasks, that it's not so varied, then you don't get maybe these benefits. And there's been less exploration in this direction because of that. But if we try to forget a bit more on the classic benchmarks, a bit related to what Malvin, if you were mentioning, right, like maybe we should move on. There could be more, and I don't want to share too much because I don't have a clear answer, but we do have some experiments where we were trying to play around with curriculum learning and trying to say like, hey, look, maybe these ideas from continual learning applied to when you have access to all of the data do have some value still and this is where maybe the problem is the semantics, and it changes from curriculum learning to active learning, right? Like it's not anymore when you reach that part. I'm not sure if this is something that you want to add on, or if you had any experience or work in this direction in the past years also, like.
One thing that occurs to me, I'm just building on, I'm sorry if I got something wrong, but one thing though is I think in active learning, partially, maybe curriculum learning a bit more, is you have a sense of information better, like how much information something holds for you. But in continual learning, none of the benchmarks have kept information in mind. You don't know whether the next task is going to give you more information than the previous task, less information than the previous task. Things are not really ordered that way. But when you do something like curriculum learning or active learning to some extent, you can, in some sense, control how much information the next task, in that sense, should bring to you. Right? So maybe that's one difference that I see between these at least. But in the continual learning, the vanilla way we look at it, we have pretty much no control. At least it's not something that's designed at least.
Okay, maybe we can move.
Just to add something quickly, also building on an earlier comment. Well, I do think like this pre-training versus fine-tuning paradigm does change a little bit the things, but what I wanted to say is that maybe curriculum learning can be also useful for its pre-training phase to make it more efficient, to make it better, but also to make it able to continue to pre-train without, throwing whatever we trained and retrain from scratch. So maybe this is something to dig deeper. I think we all know how costly it is to pre-train these models. Many of these computations seems to be somewhat wasteful. So if we do, select our data or order it in a more clever way, maybe we can achieve, the same goal with lower resources, which can be beneficial to many people.
I support this claim because we are doing something similar. Interpolate it works.
Nice.
Yeah, but I don't think about the deeper reason.
We will keep our eyes open then.
Okay.
So in the past, when we were discussing curriculum learning, we were also discussing the notion of self-paced learning. Yeah, that could also be something interesting. I mean, I've been not working on this, I would say, since 10 years at this point. And so, of course, the underlying model changed all the game, because with shallow models, we had other kind of approach, optimization based. So it was really, this changed pretty much the landscape. But then, maybe an hybrid, so some scalable way of also doing self-paced learning could also be something.
Interesting. Thanks. Maybe you can do another question and bring Elisa more and more to more continual learning, like.
It's been fun. So if he's convinced. So Vinshuan, we are working on more on continual learning after this.
So thanks for the insight so far. So I have a question about the role of foundational model, and also the for continual learning, also the role of continual learning for foundation models. So taking the case you mentioned before, like we still need continual learning in many like private domains, like underwater autonomous vehicles. We have a lot of private data set. We need to continuously to create the skills into the model, right? But if we think about another case, today we have pre-trained model A, which is the foundation model, and I use it for my robots. It works pretty well. It reached like 60 or 70% of the full capacity. And then tomorrow, I want my robot to do the same job, but with foundational model B, but do it better. So in this case, but I didn't save my data. So what is incremental here is actually the model. It's pretty normal, right? Like this month, last month I have that model, next month I have another model. We don't keep increase the accuracy, the performance of our application by taking a stronger model, but it's important for us to save the private data all the time. So how do we do a model incremental without the data? Do you have like any insights about this? This is an open question, but I just want to ask for your opinion about this, because it just came to my mind after I listened to today's talk. Thank you.
Yeah, actually, for this question, we have some probably relevant exploration. Also, they follow some relevant work. The primary conclusion is that we try to construct a better representation space rather than the parameter space, because the different model from different sources, a very straightforward way is to do the model soup on the parameter level, but they are not on a linear path in the model space, so the average or weighted average may not be that good. So maybe a straightforward strategy is to get the adapter or linker between the models layer and to correct some or rectify some representation space that's like a continuous fusion of the representation space. I think most of the current like the Continual work following this solution.
Yeah, I personally think that's a great idea. I think that's a great idea to. I know one of the questions we've been discussing is trying to see whether foundation models and continual learning are at odds with each other. So I do think looking at maybe jumping between foundation models or swapping foundation models on the go, on the fly, over time, seems like an interesting way to bring the two together. Yeah, that's interesting to me. And I mean, I'm not sure exactly. I still think probably we need notions of benchmarks clearly well defined. I don't know what the notion of forgetting there would be, or I mean, if both foundation models are equally good, assuming so. I mean, but only thing is they may have their inherent biases, but they may be equally good. These days, I think foundation models are maybe somewhere equally there, but they have their own biases. Maybe the metrics we use would have to measure them instead rather than the accuracy itself is a thought. But personally, I thought that was a really interesting thing.
Yeah, but this requires data set to be why, I mean, to have a large variety of concepts, you know, to really show if this brings an advantage and how you can fuse multiple representation, how you can do this in a smart manner, because I mean, of course, we do more simple aggregation. So it's kind of quite long-term thing, I would say.
No, I thought the interesting was I do think that we're probably moving towards a world where there are going to be a multitude of foundation
Yes.
models, not just one.
Yeah.
So yeah, it would be interesting to think through to see when I'm going to swap from one to the other and use the second one for my subsequent tasks while I was using the first one for my previous
But
task.
you also need to be able somehow to assess if the one is doing good or not. That
Exactly, yeah,
could be not
completely
not
agree.
that
My things need to be
straightforward.
defined. Yeah, completely agree.
Yes.
Can I?
Yeah, would you like?
Okay. It's just a point. It seems that the question has, if I understand correctly, that problem is called, compatible learning. You have two different models and you want to align them, right?
No, actually,
No.
for task A, to do ask A, I take a foundational model, I want to fine tune it. So this model, I just want it to overfit my application because I want to pursue high performance for my application now. And tomorrow I have another foundation model.
Yeah.
So I want to do the same job, but do it better. But I don't have the data I fine tuned in the previous foundational model. And for this case, the model is implementable, but we do not have the model. The data I use to fine tune my model. So in this, how can I use the previously fine tuned model to switch to another foundation? It has stronger capability.
If I understand correctly, if you want to jump across many different pre-trained models,
Without data.
pre-trained models or
Pre-trained, fine-tuned, jump, but without data.
yeah. I don't know if I correct understand.
But it's related, I think.
It's really
I think
if you have the same representation across different pre-trained models, you can do that job. I mean, it's and the task has been defined like in 2020 here at CVPR by Soato, Stefano. This is called compatible learning. You have many models. You want to continually learn, but you want to trust that you don't want to throw away data because the first model is really bad. The last one is very good and you want to align them. And the last one must cover the poor quality of the first one. So it's kind of defined, but I'm not sure it's exactly the same. So
maybe the nuance is that whenever you fine tune these models, this alignment might disappear very quickly. Well, those are aligned, they're compatible, but the moment that you are fine tuning one of them for a specific task, which is like the use case that I think that you were mentioning, very quickly it happens in these cases that you lose this alignment because there's all of these parts that were used for aligning with other models is like maybe concepts that you do not need. And when you drop them, you have like non-compatible maybe.
Yeah.
I don't know.
Typically fine-tuning is fine-tuning. I mean, the learning rate is very low. And so in continual learning, you have typically your big learning rate. But fine-tuning is you change a little bit the big model and it's a little bit different, but not so much. I mean,
I'm happy with that. Maybe I would like you to say the same things while I record it and then tell it to my students. Like, tuning is a very little.
I mean, once you have a very big model,
yes,
it's hard that you change the representation. Think about ChatGPT. There is no way with your little to change with your data. I mean, it's
I agree.
Yeah. And anyway, I have a paper in this regard.
okay, so it's advertising.
No, I'm not joking. I was not aware about talking about alignment of multiple models. So I mean, I raised the hand because of this.
No, but that means you should go to Federico.
Because the problem is already known, but it's kind of niche. So maybe it's not known. So
But is it a paper that you have in the poster session and people can go see?
Here in this one.
Yeah.
Everybody is going
So in a few minutes, everybody can just go there.
But the original definition is from a paper on 3 years ago that clearly defined what it means. Many tasks incrementally, but without forgetting. Not without forgetting that you have a techniques that you don't combating forgetting. Is that they have a nested data set. Like task one, the second task is task one plus task two.
Yeah, like a Russian
like
doll.
Joint training in continual learning. It's the upper bound. So,
interesting. Yeah.
And a point to the topic. We also have a paper in this regard from our group. We found out that paper found out that to how to use the prompt tune on one model and also applies to another model. Maybe I can that.
Indeed, prompt tuning can be like a proxy for another model to transfer the knowledge.
This is not the optimal for your problem, but it is potentially a solution.
Thank you.
And because we are almost running out of time, we will have the last question, maybe a bit short, but I thought it was a bit cheeky from the audience on the Zoom call, but I liked it. And Mohammed asked, I have been hearing about foundational models all the time from the past 2 days. What happened to Backbone? Do you consider that whenever we have all of this sequential, which, I mean, we never get into the non-stationary data, or task boundaries, but is the first task that you learn in a sequential continual learning the backbone or the foundational model of that sequential problem? Like, would you say that? Maybe we can do that as a wrap up.
That seems to me a different nomenclature for similar concepts, right? It's not necessarily different, but maybe the question is what do they mean by backbone, and how is it different from what you mean by foundation models? Maybe the difference is that before we used to have very specialized backbones that we get more and more general. Now we start with something that is already pretty general. Maybe this is one fine difference, but seems to me similar concepts.
Another aspect to me is the multimodality, right? So when we meant like really now the huge transition is that now we are really into a multimodal scenario. So that's, I guess, can explore more research. But I agree, maybe it's just a matter of semantics. I do agree.
Even I do agree it's a matter of semantics, I think, and when a backbone gets used for many downstream tasks, I think we call it foundation model. I think that's pretty much when we start calling a backbone a foundation model, when fine tune it for different tasks. I think this is semantic.
Okay. Well, thanks for joining the panel discussion. I think it was quite interesting. A lot of people maybe want to stop one of you to continue the conversation later. I assume that you will be happy to chat about continual learning during the next days. Please, one last thanks to the speakers. And now we will go back to the coffee break and the poster session, and we will come back at some time soon. That will be displayed in the screen in a couple of seconds. Thank you.
It's my second year. Actually, asked because I talked about with the TNI aspect of mentorship. Okay, I wanted to ask you if this is something
Okay, now it's unmuted here. You should be able to use this one. Remember if it goes, yeah. We'll have to get that. Okay. Otherwise, yeah. Yeah. So hi. Thanks for sticking till the end. Let me change this to another. Okay. There is no other pointer, but still fine. So I'm Gianluca Guglielmo. I'm here to present the kind of report from our CLVISION challenge. And first of all, I'd like to basically thank some companies and organizations that have helped us to basically carry on this project. First of all, Continual AI, which helped us with the dissemination of the challenge and gave us access to their GitHub page so that we could post our code that people could pull and use it for the challenge. They have also developed Avalanche, which is the framework that we've basically based our challenge on. With this. I think it's this. Oh, it's called.
Just unblock this one.
Okay. Okay. Well, then thanks also to Apple because they basically given us the prize for the challenge. Codalab, that is a great website where you can host your challenge for free. They have a lot of tools and it was very useful for us. And then obviously thanks to our affiliated institution, TU Graz, that has given us access to the servers to host the dataset and in general, some technical support. So what I'm going to talk about today is just an overview of the challenge, some details. We'll look at the leaderboard and then we'll see some of the winners' presentations, both in video format and live. And I know it's late, so don't get scared, like stuff is going to be relatively simple. We'll start from the basics and just build on why our challenge we think was important and where we hope it would have gone and where it went. So let's start from a very simple idea. So classic supervised learning, as you may know, you have your training data. If you want to use it for classification, then you pass it to a neural network or to whichever machine learning algorithm that you want to train. And then you basically, after it has been trained, you use it to predict over some test data that ideally has been sampled from the same distribution as your training data. You evaluate the accuracy, and then you have a result of how good your training process was. In incremental learning, stuff is relatively similar, but you only see a snapshot of your data at a time. So initially, you may see experience one in this case, which is also known as a task. So you can do whatever you want with this data that is presented at this time step T1. You train your neural network and then you predict over all the classes that have been seen up to that point. Then you go forward and you pass to experience 2. You don't have access to experience 1 anymore, but you are exposed to ideally new classes and new samples. And then after training again your neural network, then you have to predict over all the classes that have been seen up to that point without knowing exactly which sample comes from which experience, which is a condition known as task agnostic. Then you continue and you get what's known as a stream of data. So to sum this up, incremental learning is just a process where you have no access to classes of already learned experiences, and then you evaluate over classes that have been seen so far. So this is pretty straightforward. What happens, as you may know, is that you get this catastrophic forgetting where
the classes that you've seen for last usually have a higher accuracy. Initial classes have a lower accuracy, and this is because, to sum this up, just the neural network concentrates on last data and kind of overrides the weights that it had learned in the past. So this is basically a performance loss, and it requires a balancing of these two concepts, which are plasticity, so the openness to learning new classes, and stability, which is instead not shifting from what you already have learned. And then incremental learning has a subset of it, which is incremental learning with repetition, where you may experience classes that you have seen in previous experiences. Like here, you see again this red squares that you've seen in experience 1. But the thing is that not all training samples may be available in a single experience. So the question could be, how do you, I'm sorry, yeah. Okay, no, wrong slide. Anyway, I'll first talk about this. So another subset of incremental learning is incremental learning with unlabeled data, which is what we wanted to concentrate on for the challenge. So ideally you have two streams, and a stream that is labeled, so the standard things you receive in an incremental learning setting. And then you also have an unlabeled stream, which is paired experience by experience with your labeled stream. And then you basically want to evaluate after each experience over all the classes that have been seen in the labeled stream up to that point. So in this case here, we see this square and circle. And then here we just add the star and the triangle and so on and so forth with the other shapes. So at each experience, you evaluate over all the classes that have appeared up to that point. But the question is then, what's this unlabeled data? That's a good question. So it can come from two kind of types of classes. So from seen classes up to that point. So they could be samples that you've already experienced. So it could be that if you are in experience 2 in the unlabeled stream, you may see again this sample here, or it could be new samples. So if you're in experience 2, you may see these samples that will appear later in the future. Or they can be from unseen classes altogether. So from novelties, so classes that you will eventually at one point meet in the labeled stream, or from distractors, which are things that are completely out of distribution, will never appear in your labeled stream, and will just distract you from your main task. So this is what our challenge built on. And to go more into details, we had 2 phases here. Sorry. The pre-selection phase that started in February, we've developed 3 scenarios, which are basically 2 pairs of streams, call them 1, 2, and 3 simply. And then we had a final phase where we selected the best performing methods and applied them to slightly more difficult scenarios 4, 5, and 6. To give you some stats, well, we had 87 registrations to the challenge, 24 plus participants, because plus means that some of them were teams, so technically more people were participating for each kind of user. And then 340 submissions in total. There was a cap at 50 submissions per user. And the setup, as I've just described it, is that you have 2 streams per scenario, so the labeled stream and the unlabeled stream. You have 50 experiences per stream. And then in order to simulate a real-world scenario where unlabeled data may be cheaper, and also to encourage people to exploit this unlabeled stream, even though it was not necessarily required by the rules, we gave more samples to the unlabeled for each unlabeled experience than for each labeled experience. And then the main metric that we simply used for to create the leaderboard was the final accuracy at the end of the last experience. So as I said, there were 3 scenarios for each phase of the competition. So I'll briefly describe them because each of them has a different kind of nuance to it. So in scenario 1, which is the simplest scenario, you have that the labeled stream matches the unlabeled stream 1 to 1. So in order to interpret this plot, here on the x-axis, you have the experience or the task. And here on the y-axis, you have the class. And if you see a colored box, it means that at that experience, you meet that class there. So in this case, the labeled stream contains the same classes as the unlabeled stream. So it can be relatively simple for somebody exploiting the unlabeled stream to know that everything you see in there will match the labels that you will see at each experience in the labeled stream. Then in scenario 2, we have again this correspondence. So it's probably not that clear to see, but again, each class in the labeled stream is represented in the unlabeled stream. But additionally, we also have classes from what I earlier defined as novelties. So classes that you will see eventually, but you haven't met up to that point. This data can be used for prototyping. So you can basically create your initial idea of what that class could look like in the latent space, or kind of save it in a replay buffer and apply it however you want to your approach. Then we have scenario 3, where instead there are the distractors. As you can see here, all these classes appear, and in the label stream, they never appear. So they are there to, as the name says, distract from the main task. Scenarios 4, 5, and 6 for the final phase are basically based on scenarios 1, 2, and 3, but they add some kind of difficulty to it. Specifically in scenario 4, we have again this one-to-one correspondence, but we have more classes, so 110 classes in total, 55 tasks. Scenario 5 has that the density of unlabeled classes increases throughout the stream. So initially you have just a few classes, so it may be harder for prototyping, while at the end you'll see more and more, but just after you've met that specific class. Depending on how your approach is structured, this could be easier or harder, depends on what you do with this unlabeled data. And scenario 6, as with scenario 3, has these distractors, but in this case, we simply have more distractors. So there is a higher ratio of distractors to non-distractors. So the restrictions were kind of straightforward for us to implement. As with every incremental learning setting, you are restricted to only using current experiences data. You can't save anything. You can't save samples, sorry, from previous experiences, and you cannot take a look at later experiences. Each strategy has to work for the 3 scenarios, and this is done so that we test basically the generalization power of the approach. You can't tweak hyperparameters. You can't change any magic number from one scenario to the other. The model architecture is simply a ResNet 18, not pre-trained. And we also allowed for people to use a replay buffer of exemplars only, not samples, meaning that you cannot store entire images, but you can store any kind of hidden representation or prototype that you may see fit, up to 200 of them. And this is something that is usually implemented either for memory saving or for privacy preservation, so that you don't store necessarily data for a long time and you basically forget about it, but you don't forget about the information that the data can give you. So now we can look at the leaderboard. Now the results went. So this is the pre-selection phase. We had implemented a baseline, which is just learning without forgetting, that had a 9.39 average accuracy over the 3 scenarios. We had, fortunately, several teams beating the baseline. Specifically, the team and just KMG had a 45.3, then we had 41.2, and so on. So pretty good results overall. We then contacted these first 10 teams. Some of them decided not to continue. Some of them simply did not respond. So in the end, we basically selected these 4 teams and first checked their code so that we noted, so that we could test that all the restrictions were being followed. and also that we could reproduce the results that were in the leaderboard. So for the final phase, applied on scenarios 4, 5, and 6, we have that as it was predictable, the order basically stayed the same. And NJust KMG basically won with a 48.1, showing that actually the last 3 scenarios were simpler than the first 3, because overall the average accuracy increases for all the teams. So now, well, I don't know if you have any questions. Maybe we can stop for a few minutes and then we can look at the winners' presentations. Not sure. Is there any question from the audience? Or the setup? Okay, then let's move on. Okay, yeah, we can. So now we can look at how the teams have tackled the problem. So let's start from the 4th place. We have this team from Greece, team PMEK. They are affiliated to the University of Thrace, the Athena Research Center, and the National Technical University of Athens. They have sent us a video that I will now show you, where they here.
Hello everyone. We would like to thank you for giving us
okay, wait. Share. I'll share the whole screen. Can you see now?
the opportunity to present our solution for the 5th CLVISION challenge. My name is
yeah, the audio is coming out from here.
Yeah.
There had to be another technical issue. And you're not sharing the audio. No, but the problem is that the room does not hear it. If you go here. Here. Try again with real. Yep.
At the National Technical, giving us the opportunity to present our solution.
No, I think it's an issue from here. Okay.
Archimedes unit.
Oh, yeah, you can do that. Microphone on. Good. Yeah. Let's see if this works. No. Yeah, I don't know what's going on. Let me try with that cable there. Okay.
Hello everyone.
Yeah, that cable just decided not to work. Yeah. All right, so here it is.
We would like to thank you for giving us the opportunity to present our solution for the 5th CLVISION challenge. My name is Karipidis Evstathios and I am a PhD candidate at the National Technical University of Athens, as well as a Fellow of Archimedes Unit. My supervisor is the Assistant Professor Nikos Komodakis, and my main research interests include large-scale unsupervised learning and foundational models.
Hi everyone, my name is Panagiotta Moraiti and I am an undergraduate student at Democritus University of Thrace. I am currently working on my thesis titled Continual Learning for Domain Adaptive Object Detection under the supervision of Professor Ioannis Pratikakis.
This year's challenge focuses on the class incremental learning with repetition problem. As a second aspect of this problem, participants are encouraged to utilize unlabeled data to enhance their model. The key characteristics of this problem include the arbitrary reappearance of previously observed classes and the availability of only a portion of the total number of classes in each experience. Based on the classes to which the unlabeled data belong, there are 3 scenarios as specified on the challenge website. Our strategy was inspired by 2 well-known regularization methods and was applied to both labeled and unlabeled data. The learning without forgetting method aims to mitigate forgetting by applying knowledge distillation. The second regularization method we incorporated in our strategy is based on less forgetful learning. Specifically, we applied an auxiliary loss to maintain the feature space and prevent significant changes when encountering new data.
Now, let's continue with our approach to further exploit the unlabeled samples. As a first step, we extract a feature prototype for each class within the labeled data. Moving on, for every unlabeled data point, we generate a pseudo-label using the pre-computed feature prototypes based on a similarity metric. However, in order to remove misleading labels for samples that might belong to unseen classes or distractor classes, we introduce a filtering step using a similarity threshold. Finally, we utilize soft cross-entropy loss between the pseudo-labels and the predictions of our model. When encountering unlabeled samples from previously seen classes, this process helps minimizing forgetting.
I think it's every half an hour that the microphone is on, this cable slides.
Yeah.
Our model. When encountering unlabeled samples from previously seen classes, this process helps minimizing forgetting. Regarding the training hyperparameters, we limit the number of training epochs to 15 and incorporate early stopping to prevent over-specializing to current classes. To further boost the performance of our model, we use a learning rate scheduler. Here you can see the overall pipeline of our method and especially how each loss term is computed. Starting from the input, each sample is passed through the model and a frozen distance of the model from the previous experience. Apart from the standard cross-entropy loss between model predictions and ground truths, the LWF loss penalizes the difference of the softmax outputs, while the LFL loss encourages similar features. As a final component, The soft cross entropy is computed using the pseudo labels and is added to the total loss. In this slide, we present the results of our team. As you can see, our approach significantly boosts the performance in scenarios 2 and 3, where the unlabeled data can contain samples from previously seen classes. Also, since the labeled and unlabeled images belong to different classes, this leads to an increased number of past classes in each experience, which is crucial to reduce forgetting.
Thank you for your attention.
All right, so we then have the presentation from the third place, the team that arrived in third place, which is team STUN AI from China, which have also sent us a video.
Hi everyone, we are from China Telecom Cloud Company. We will be presenting our work titled Frequency Aware Loader and Feature Supervise in Class Incremental with Repetition. This article is a technical summary of our participation in the 5th CLVISION Challenge. It is our first time participating in the CLVISION Challenge, and we achieved 3rd place in the challenge. Our solution features 4 key parts to enhance learning effectiveness and results. It starts with diverse data, including labeled data for guidance and unlabeled data for pattern discovery, plus 1024D feature vectors for deep comprehension. Next, the replay loader uses a smart storage plan adjusting to data frequency, addressing class imbalance in cases for balanced learning. Our model design uniquely combines new and old model insights, using cross-entropy loss for labeled data with label smoothing and a dual strategy for unlabeled data, which aligning feature after full connection layer outputs between models via distillation loss to prevent catastrophic forgetting. Additionally, we meticulously compare and quantify differences in full connection outputs for feature retention. Overall, our method's synergy showcases innovative data handling, learning tactics, and model tuning, with remarkable adaptability and practical efficiency, presenting a pioneering solution for complex, dynamic data challenges. In the 5th CLVISION Challenge competition, our team's performance was remarkable. During the preliminary selection stage, with an impressive score of 23.91, we ranked 5th, successfully advancing to the final round. Following this, after rigorous reproduction verification by the organizers and meticulous training on the final phase dataset, we ultimately achieved an outstanding average precision score of 29.15, earning us the 3rd place position and highlighting our team's formidable strength and exceptional ability in algorithm optimization. In the pre-selection stage, we thoroughly tested various strategies to boost task accuracies. We started by modifying our base model, removing past experience cues, causing a 2.4-point drop, but setting a benchmark for improvements. Implementing the replay loader marked a pivotal moment, single-handedly raising scores by 8.5 points, demonstrating its effectiveness against data forgetfulness. We also tried calculating loss based purely on class features, adding roughly 6.8 points independently, emphasizing the importance of detailed feature management in model enhancement. Combining the replay loader with feature loss calculations was highly effective, elevating our model's precision to 23.913, a significant 14.5-point jump from the original baseline. This exploration and refinement process showcases our deep comprehension of the challenge and our strategic innovation and optimization capabilities. In summary, 3 essential points stand out. We use a novel strategy with a frequency-aware storage system for the replay loader, which adjusts buffers to tackle class imbalances, greatly improving recognition accuracy across categories. Evidence shows combining new and old model learning dramatically reduces knowledge loss between tasks, supporting ongoing learning and strengthening the model's progressive development. Class feature vectors act as additional supervision, reinforcing the model's hold on all category data, reducing category forgetting, and thus enhancing generalization and retention capabilities.
All right, so now we have the second place, which is a team from Korea, specifically from Seoul National University and Yonsei University. So I'd like for Sun to come here, present.
Oh, yes.
Oops. Actually,
yeah.
Can you go to this? It's okay. Like they can read the presentation. Even if people are not. Okay. Yeah, so I'll just send you yeah, how do we do this? You go to the CLVISION website and there's Are you logged in the CVPR?
Yes.
Okay, and can you go to CVPR? Actually, to the CLVISION website? Yeah. Yep. Where's the link? Yeah. 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 Okay. Let's join. Chat. Perfect. No, it's good because the audio comes from here. Test.
Hello, my name is San Kim from Seoul National University. Hyun Kim, Minhyuk Seo, and Professor Jong Choi work with me. Today, I'm here to present our team strategy for this challenge of O-level included class incremental learning with repetition.
Try to maybe share it. Share it again. No. This one. Yeah, you did.
Okay. Yeah, like this. Sorry. Here's our motivation. To maximize the use of previous model information in situations where the class distribution is unpredictable, we came up with an advanced distillation method. Considering that the number of samples in O-level stream is more than that of lava stream, we found the most appropriate self-supervised methodology within the challenges regulation. First of all, we use a simple yet effective ERH method as a baseline. This baseline difference, the only difference from the original cross-entropy loss is that for stream sample, it calculates the cross-entropy loss only using the classes existing in the stream sample. Also, since we cannot store the sample themselves in the episodic memory, we store a 512 size dimension feature vector by passing the FC layer. To alleviate catastrophic forgetting in continual learning, it is crucial to distill knowledge from previous models. Our multi-level knowledge distillation involves distilling knowledge from multiple perspectives with multiple previous models, utilizing both feature distillation and logic distillation. We experimentally confirmed that using 3 preceding models is efficient. For feature distillation, we apply L2 loss to each of the 3 preceding models. In the memory feature vector, we applied L2 loss only passed by the FC layer, similar to the DER approach. Reference to the below paper. In logic distillation, naively distilling by instance-wise comparison is harmful, as the logic weakly reflect the knowledge of trained data. To account for this problem, we use gram metrics to capture the correlation within batches and across classes, similar as reference to the below paper. In addition to knowledge distillation, we incorporate self-supervised learning using on-level dataset to foster the model's plasticity, enabling it to adapt to new concepts effectively. Among various methodology, we used rotate prediction, which showed the best performance through experiment. It is literally a task of predicting degree of which an image has been rotated. However, a naive application can degrade the performance of the primary task, since self-supervised loss can degrade the performance of the primary task, as self-supervised loss does not directly align with the target task objectives. To balance with this loss on the model's learning process, we applied dynamic weighting to self-supervised loss. So here's our method overview. We gradually update all previous models using exponential moving average manner with current model, and use this previous model in multi-level knowledge distillation. And we dynamically reduce self-supervised loss as hyperparameter, ensuring the model remains focused on the primary task while still benefiting from the generalization ability of self-supervised loss. So our approach's necessity is presented in this table. We also experimented with various other state-of-the-art self-supervised learning methods other than rotate prediction. As shown in this table, this method performs worse than simple rotate prediction. We assume this is because these methods require a large batch size and longer training time to be effective. Thus, complying with the challenges restriction, this contrastive-based method lead to suboptimal performance. Finally, we compare the performance with and without using dynamic weighting when applied to self-supervised loss. We can see that the constant influence of self-supervised loss in the learning classification task and dynamic weighting could mitigate this problem. This is that we all did. Thank you for listening to my presentation.
Thanks a lot.
Oh, yeah.
Is there any question from the audience that we have here?
So the first place, as I said, is from Team NJUS KMG from Nanjing University of Science and Technology in China. They have also sent us a video that we can watch together.
Hello, everyone. Hello everyone, we are the NJST KMG team from Nanjing University of Science and Technology. I'm the team leader, Sishun Pan. It's a great pleasure to share with you our solution in this competition. In traditional class incremental continual learning, the class in different series are not overlapping and only label data is available. However, in this computation, the class in different scenarios may repeat and a more realistic and challenging open environment with semi-supervised setting has been introduced. Facing the dual challenge of repeated class and a large mountain of unlabeled data, we have devised a series of solutions. Regarding the model, we use the parameter-isolated method, but did not employ HAT. Instead, we use a more advanced approach, the Wiener subnetwork. WSN evaluates the importance of parameters and automatically selects the more important ones for learning. Through network reuse, it better transfers knowledge from previous tasks, and by using masks, it isolates the update to the weight of previous tasks, thereby avoiding forgetting. We have made an innovative improvement to WSN by modifying the parameter importance update method, making parameter selection more reasonable and flexible, and improving the model's learning performance. During the training phase, we separated the learning of labeled data and unlabeled data. For labeled data, we use concentric loss for learning. And for unlabeled data, we have devised two strategies. First, we use unsupervised contrastive learning method by applying weak and strong data augmentation to the sign images. By using contrastive learning, we bring closer the distance of the sign image and push apart different ones, enabling the model to learn generalized features. However, this alone does not fully utilize the unlabeled data. Drawing from the ideal of fixed match, we introduce a pixel labeling method to better use of the unlabeled data. Specifically, we apply weak and strong data augmentation to images. If the model's product logics for weak augmentation images exceed a certain threshold, we consider the model capable of making a reasonable correction production and generated corresponding pixel labels. These pixel labels are then used to learn from the strong augmented images. This method is simple yet effective, significantly increasing the amount of pixel label data during training, with up to 80% of the unlabeled data being pixel labeled. This demonstrates our full utilization of the unlabeled data. Despite potential overconfident issues, most OOD samples logics remain below the threshold, thus avoiding excessive inclusion of OOD samples in learning. Consequently, our method performs excellent not in scenarios with only ID data, but also in the scenario 2 and 3. During testing, we leverage the characteristic of overlapping classes in different scenarios. We pass the samples through each subnetwork, obtain the product logics for all classes, and averages the logics for each class as a final production. This effectively addresses the issue of parameter isolation method being unusable in class incremental continual learning. Experimental results show that by fully utilizing unlabeled data, our performance has significantly improved compared to using only labeled data. In the final testing phase, our method exhibited excellent generalization performance across all 3 scenarios, automatically achieving first place. This concludes the presentation of our team's solution for this computation. Thank you all for listening.
All right, so we've seen the 4 presentations, and just like to conclude by saying thanks to all the participants. Congratulations to the winners, and just by pointing out that Benedict and Mark and me are here. So if you want, you can talk to us, we can discuss. And in general, also thanks to Lama and Hamed that have been part of the organization team, both for the challenge and the workshop. Thanks a lot. Yeah, Astrid will be here the rest of the conference. So if you want to talk about continual learning with repetition and labeled data and so on, like, we are available. There was a question?
Do you have the code available online for all these?
I believe that most of the participants will be fine with sharing their GitHubs whenever they have a final version, because they've shared it with us, but we have to talk with them and then we will see. There was a dev kit that was provided for the challenge, so most of them follow that setting, so it should be.
That kit is still online, and also we'll publish the scripts for evaluation, so in case you want to try continually to improve the results or just play with it, it will be available also.
Yep. Okay. And now, so for the last part, and second, hold it. Before we go into the last talk of the day, the oral presentation, we also would like to go for the best paper award. So drum roll, please. From the 2 oral presentations, the talk that will happen now is actually the one that was decided by the reviewers and meta reviewers to have the highest score from all of the submissions. There were actually pretty much a lot of very good submissions that were fighting, and congratulations. I mean, you will give the talk, but also we will to let you know that you were given the best paper award. So I will send a PDF version that you will be able to bring your award. So please, if you would like to come pick it up. Would you mind taking a picture? And now maybe you can share with us a bit the is this one? Share it. Yeah, it should be. Let me double check it. Yes, it's not active. Okay. So keys, or do you want to unlock?
No, yes.
Perfect. So the floor is yours.
Okay. Hello. Thanks everyone for sticking till the last presentation, and thank you very much for the award. I have not expected. Yeah. So let's jump straight into it. I'm Jędrzej Kozal, and I'm a PhD student at Warsaw University of Science and Technology, and I want to talk about my paper, Continual Learning with Weight Interpolation. So first, neural networks have this property, which is called permutation invariance. It means that we can change the order of units, either in kernels in convolutional neural network, or the neurons or the rows in the matrix in the linear layer. And if we do that in proper way, which is guided by these equations for multi-layer perceptron, then the output of neural network won't change for given inputs. And this property was used in weight interpolation algorithms such as Git-rebasing or repair, where we search for such interpolation that would allow for aligning the either weights or the activations of two neural networks with the same architectures that were trained with different random initialization. And it turns out that if we find such permutation and apply it to the neural network, then if we do the weight interpolation between such networks, then we do not have loss barrier between these two, because these two solutions end up in different local minima as they were trained with different random initialization. If we do weight interpolation without this permutation, the loss value would increase significantly because we would end up in the area between two local minima. And if we apply this permutation, then we transport one of the solution to the other local minima. And we wanted to utilize this property in continual learning because in both Git-rebasing and repair papers, it was found that even if these networks were trained on different subsets of given data sets, the weight interpolation could still work. So idea here is quite simple. We want to store weights after training with first task. Then we train with some new data with different data distribution. And after that, we want to interpolate this previously stored weights and the neural network that we have trained on latest data. And however, there's the assumption in the weight interpolation papers, namely both of these solutions have to be in the local minima. And this does not necessarily have to be true in continual learning. So here's the simple example. At the top, we have the loss landscape for first tasks. When we finish training, we will end up in, excuse me, we will end up in some local minima for that particular task. However, when we have a second task with different data distribution, then entire loss landscape changes. And if we train with that task, the main source of updates to our in our SGD is the data from the second task. And we end up in some local minima for that second task, but we have no guarantee that we will be in the local minima for the first task as well. To be more formal, in continual learning, we are interested in optimizing this joint loss, which is the sum over all of the losses for all tasks. But we do not have access to previous tasks. We only have access to the data from the latest tasks. we can define this delta L as the increase in the loss value. So the difference between the loss evaluated after training with that task and loss evaluated after training with all of the tasks. And now we can rewrite this joint loss function as this sum of the loss directly after training, which corresponds to plasticity, and this delta L, this increase in loss value, which corresponds to forgetting. And now we can see that if we want our model to be in local minima, we must have both high plasticity and low forgetting. And to obtain that, to guarantee that, maybe not guarantee, but to make sure that our model is at least close to some local basing of minima from previous tasks, we simply use memory buffer based algorithms. So the idea is really simple. First, we do standard training with memory based algorithm. Here it is vanilla experience reply, but in principle, our solution could work with many rehearsal-based algorithms. And then after first task, we store the weights that we have learned. So this is this theta p. And after that, we, on the second and each next task, we train with this experience reply or something similar. And after that, we calculate this permutation pi. We apply this permutation and do the weight interpolation to obtain the new set of parameters. And then we update batch normalization. This is the step that was introduced in repair weight interpolation algorithm that we used as base of our paper. And after that, we also store this model for the next weight interpolation after the next task. So you can see that what we have proposed here is a plugin that can be used with many existing memory-based algorithms. And we did experiments on these three datasets that are commonly used in architecture, and we use a standard set of metrics. We used ResNet 18 architecture with buffer size 500. And when it comes to results, we can see that both in terms of average accuracy evaluated after training with all tasks and forgetting measure, in most cases, the proposed method improves the performance. The highest performance increase could be observed for vanilla experience reply or maximally inferred rehearsal, which are pretty simple experience reply forms. And more sophisticated methods, such as bias correction or dark experience reply, do not enjoy such a great improvement. This could be due to the case that these methods limit the plasticity to combat the forgetting. So they may be not so great a difference between the two neural networks that we are interpolating. In our paper, we also do these interpolation plots, which are the test accuracy as a function of interpolation alpha, which is hyperparameter in our algorithm. And here at the left-hand side of this plot, we have newer model, which was trained with most recent task. And at the right-hand side, we have a previous model that was stored. So we always evaluate with all of the classes that were seen by the newer model. So this means the newer model should have better performance, at least in the beginning, because it's seen more classes than the older model. And this could be also the reason why the local maxima of accuracy is shifted towards the left-hand side. And as the training progresses and we are adding more tasks, the local maxima is shifting towards the right-hand side. And if we use higher values of alpha, so we move towards the right-hand side, we are prioritizing more the forgetting prevention. This could be also seen in this table on the right-hand side, where we see the final accuracy at the end of training. We see the accuracy at the of the latest task and forgetting measure. Here we can see clearly that with low alpha, we obtain highest accuracy on the last task, but we also have a high forgetting measure. On the other hand, if the alpha is higher, then we have low accuracy on the latest task, but also low forgetting. So this alpha allows for direct control of stability plasticity dilemma. So in summary, weight interpolation should not be used as a sole source of forgetting prevention. We tried that in our preliminary experiments, and we have a really simple theoretical analysis when we show that this should not work. And it could be combined with memory-based algorithms to improve the performance. However, there are some caveats, and you need to be mindful about how you do that, because if your algorithm has some actions that are taken after training with given tasks, then the weight interpolation could interact with it, and it could break some stuff. So if you want to use it, please be mindful of that. And as we have also shown, our proposed method allows for direct control of stability plasticity. So this is all. Thank you for your attention, and I will gladly answer your questions.
Any questions from the audience? Okay. I have a couple of questions, if it's good.
Yeah, sure.
The first one is when you were talking about the pi, like the permutation, this is based kind of like is as good as the data that you might have on previous tasks. No? Like, is it dependent that like finding a good permutation is dependent on the amount of data that you can access from previous tasks, or is it completely independent?
In some way, it is dependent because I think the best results in weight interpolation could be done with, could be achieved with activations. And for calculating the activations, you need to have accurate representations of tasks. And that's why we are using the memory buffer to calculate these activations that we can then later use to calculate that pi. In principle, pi is obtained via Hungarian optimization. Mm-hmm. So we want to know which kernels in convolutional neural network we want to switch. But the activations that we use that if we have more accurate representation, then sure, then it helps for the interpolation.
Because for me, it reminds me also in some aspects on some rotations that we were also calculated based on activations. Mm-hmm. And then I was wondering if you have an intuition on whenever you have this experiment. I mean, first, maybe whenever you have done these experiments, maybe on Cypher-10 or something like it's more controllable or explainable, do you notice that the shift permutation or no permutations, like do you see that there's very much shift on the earlier layers? Because maybe there in some of these cases where your distributional shift is very low and it's more towards the outputs, would it be possible to just freeze certain layers where you do not do any permutation, but also you don't do any adaptation and still be able to achieve? Or you're depending that the whole model requires to be permuted? Like, is there like the same that you could have worse activation samples or more noise in your activations, and therefore your permutation will be less good? Would that be achieved by maybe freezing some of the layers, so that will introduce a bit of noise on the others, but it will allow you to not have to store the images, but intermediate representations, achieving privacy preservation?
Mm-hmm. Maybe that's achievable. but I would actually go other way around. So interpolate the layers that are at the very bottom. Why? Because actually, after we have submitted this paper, or maybe around the same time, there was on arXiv, there was new weight interpolation method published, which is called ZipIt. And there they interpolate only up to certain layer from the beginning to some layer. And after that, they keep multiple heads. And it turns out that it works much better. Maybe not much better, but significantly better, right? So this could be one direction that could be done here. And from transfer learning literature, we also know that sometimes the activations or features in the early layers are better for transfer learning. So maybe we could be better off with interpolating only the first layers. But I think what you proposed to maybe interpolate only the later layers could also make sense when we think about privacy preservation, because that's the problem that we could have here. Essentially, it's all about the activations, because interpolation with weights alone does not work that well. But if we would get around the problem of having to recompute the activations, then it should work.
I think the reason is exactly what you were saying now. The earlier layers are usually good for transfer learning because they are generalistic, and therefore you might be able to solve the problem without needing to change or changing very little. This was but it's very interesting the other way around. I wonder if for continual learning, maybe having these multiple heads might become something that it's just a scalability issue, but it works better. Like I like the idea. Thank you for any further questions? Okay, then let's find the speaker. And with that, we conclude the workshop. So thanks a lot for attending. We hope that you have enjoyed it and it has inspired you or motivated you to continue or start in the continual learning world. And as we've been repeating, most of the invited speakers, us as organizers ourselves, some of the oral speakers, I hope that I don't overstep, but I think we are all very passionate about what we do, and we will be happy to discuss more ideas on the next days of the conference. So thanks again for coming, and until next year, probably.